Hello there, and welcome to the Cosmographer. On the morning of the 28th of August, 1686, the director of the Paris Observatory watched a crescent-shaped object sit beside Venus for 15 minutes, and it took 201 years for anyone to work out what he had actually seen. Number 8 on this list is a comet that split in half in front of witnesses in 1846 and now arrives only as dust from a passage it made in 1649. Number 6 is a disk of planet-building material that lost all but a trace of its infrared light in under 2 years, while the star it orbited did not flicker once. Number 5 is a nebula whose brightest line has fallen by a factor of 900 since 1990. And the object at the top of this list is a whole 24,000 light-years across with nothing at the bottom of it. Over the next 3 hours, we count down 10 objects that were observed and catalogued and are not there now, ordered by how much of our picture of the universe has to stay unfinished because each one is gone. Get comfortable and settle in. If long, careful walks through the universe are how you like to end the day, a quiet like and subscribe helps this channel reach more people like you. Because by the end of this list, the sky stops looking like a finished picture. Let's begin at number 10. Number 10, the moon of Venus that never existed. There is a particular kind of problem in astronomy that almost never gets talked about, and it is the one this entire list is built from. When something new appears in the sky, the whole apparatus of the science swings into motion. Alerts go out across the networks. Large telescopes are redirected within hours. Spectra are taken, light curves are assembled, papers are written, and within a season the object has a name, a distance, and a place in a catalogue. Astronomy is extraordinarily good at appearance. Disappearance is a different matter entirely. When something that was already there stops being there, none of that machinery works, because there is nothing left to point at. There is no light to spread out into a spectrum. There is no shape to resolve. There is no follow-up target, because the target is the problem. All that remains is the record of what used to be, and the record is always thinner than anyone would like it to be. So this is a countdown of 10 objects that astronomers observed, measured, catalogued, and in several cases photographed, and which are now not there. Every one of them is documented. Every one has names attached, and dates, and instruments, and numbers. Nothing on this list is a rumor dressed up as a case file. They are not ordered by size, and they are not ordered by distance, and they are not ordered by how strange they sound. They are ordered by how much of our picture of the universe has to stay unfinished, because the object is gone. How much left with it? How much we would have to rewrite if we ever found out where it went? That is the ladder we are going to climb, slowly, over the next 3 hours or so, and it happens to climb in physical scale as well, which gives it a second quiet shape you will feel without my pointing it out again. And we are going to start with the honest baseline, because the first entry on this list is an object that was reported by some of the finest observers in Europe, repeatedly, across more than a century, and which never existed at all. Between 1645 and 1768, a satellite of Venus was reported roughly 30 times by around 20 different observers, in Italy, in France, in England, in Germany, and in Denmark. In 1884, it was given a name. It does not exist. Venus and Mercury are the only 2 planets in the solar system with no natural satellites, and no spacecraft ever sent to Venus has found the slightest trace of one. The first claim came from Francesco Fontana, a Neapolitan lawyer who had turned himself into a telescope maker in 1645. He published it the following year in a book with the title Novae Coelestium Terrestriumque Rerum Observationes, which carried 27 etchings of the Moon and 26 woodcuts of other bodies, and was the most heavily illustrated astronomical book of its time. In that same volume, Fontana also announced extra moons around Jupiter and around Saturn. Those were wrong as well. On its own, the claim would have died there. What kept it alive was the man who took it up next. Giovanni Domenico Cassini was the director of the Paris Observatory. He discovered 4 of Saturn's moons. He found the gap in Saturn's rings that still carries his name 3.5 centuries later. He was, by any reasonable measure, the most careful planetary observer alive. On the 25th of January 1672, Cassini logged a small object near Venus and said nothing about it publicly. 14 years later, he saw it again. On the morning of the 28th of August, 1686, using a telescope of 34-foot focal length, Cassini recorded an object beside Venus, and this time he wrote it down formally and announced it. The object showed the same crescent phase that Venus showed. It appeared about 1/4 of Venus's diameter, which is exactly the sort of proportion a real satellite might have. And it stayed with the planet. Here is what that morning was like. It is not yet dawn in Paris, and Cassini is at the eyepiece of an instrument that is longer than a house. Venus sits low in the eastern sky, a hard white crescent, bright enough that looking at it directly leaves an afterimage. Beside it, offset by a small distance, is a second shape. Not a point of light, which is what a star would be. A crescent. The same crescent, lit from the same side, smaller. The two of them hold their positions relative to each other while he watches. He watches for about 15 minutes. Then he steps away from the eyepiece, for reasons his notes do not record, and he is gone for 5 minutes. When he comes back, the eastern sky has brightened past the point where the fainter object can be recovered. Venus is still there. The other thing is not. He never sees it again, and he dies in 1712 without an explanation, and his notes are compiled and published after his death by other people. The list of observers who followed him is not a list of amateurs. James Short, the Scottish optician and Fellow of the Royal Society, reported it in 1740. Short built roughly 1,370 parabolic mirror-reflecting telescopes in his working life, and his instruments were considered the best in Britain. Joseph Jérôme Lalande cited Short's sighting in his own textbook of astronomy in 1764 as credible evidence, while noting his own doubts. Andreas Mayer, a mathematician and cartographer at the University of Greifswald, reported it in 1759. And Joseph Louis Lagrange, the Lagrange whose name is on the 5 gravitational balance points that spacecraft use to this day, is credited with an observation in 1761, and went so far as to announce that the satellite's orbital plane stood perpendicular to the plane of the solar system. 1761 was the peak year, and there is a straightforward reason for that. It was a transit year. Venus was going to cross the face of the Sun, an event that happens twice in a century and then not again for more than 100 years, and every telescope in Europe was pointed at the planet. 18 separate observations of the satellite were reported that year by 5 observers. Jacques Montaigne of Limoges read memoirs describing his sightings to the Académie des Sciences in Paris on the 21st and the 27th of May. Armand-Henri Baudouin de Guémédeuc read a paper to the Académie Royale on the 20th of May with the title Memoir on the Discovery of the Satellite of Venus. During the transit itself, on the 6th of June 1761, Abraham Schouten reported a small dark spot trailing Venus across the disk of the Sun. That would have settled it. A moon crossing the Sun behind its planet is not something a telescope can invent. Except that Samuel Dunn, watching the same transit from Chelsea in England, saw nothing of the kind. Two competent observers, the same event, the same afternoon, and only one of them saw the thing that mattered. Jean-Laurent d'Alembert wrote to Voltaire about it afterwards, with the driest possible summary, saying that the moon had declined to follow its mistress during her passage over the sun. Frederick II of Prussia proposed that the satellite be named after d'Alembert. D'Alembert declined the honor. He did not believe it was real, and he preferred not to have his name permanently attached to something that might not be. The last serious campaign was Danish, and it produced the most human document in the whole affair. On the 3rd of March, 1764, Peder Roed-Kjær observed an apparent companion to Venus through the telescope in the Round Tower in Copenhagen. Christian Horrebow confirmed it a week later, in front of witnesses, and afterwards wrote a sentence that is still worth reading 2.5 centuries later. "Never," he wrote, "have I seen in heaven any vision that has consumed me more, and I believed that I really saw a Venusian moon." Sit with the shape of that sentence for a moment. He does not write that he saw a moon. He writes that he believed that he really saw one. A careful man, at the end of a week of confirmation with other people standing in the room, recording his own certainty in a form that leaves a door open. He was right about being consumed and wrong about everything else, and he could not have known which was which. Horrebow made the last claimed sighting of the classical era in 1768, and then the reports stopped. The explanation arrived while some of these men were still alive, and it came from Vienna. In 1766, Maximilian Hell, director of the Vienna Observatory, published a treatise arguing that every one of these sightings was an optical illusion produced inside the telescope. Venus, he pointed out, is brilliant. It is the third brightest object in the sky after the sun and the moon. Its image is bright enough to reflect off the surface of the observer's own eye, travel back up into the eyepiece, bounce off a glass surface, and return to the eye as a second, fainter image, offset slightly from the first. The modern account is very close to what Hell proposed. Internal reflections at the eyepiece and objective surfaces, together with diffraction, produce a faint secondary image of a bright object. And here is the detail that made it so persuasive for so long. A ghost of Venus is a ghost of Venus. It carries the crescent shape, lit from the same side, because it is made from Venus's own light. It looked exactly like what a real moon would look like, because it was made of the same photons. The name came later, and from an unexpected direction. In 1884, Jean-Charles Houzeau, formerly the director of the Royal Observatory of Belgium, revived the whole subject with a different idea. He proposed that the object had never been a satellite at all, but an independent small planet orbiting the Sun on its own, with a period of 283 days, coming into conjunction with Venus roughly every 1,080 days. That spacing, he argued, matched the pattern of the historical sightings. He gave it a name. He called it Neith, after the Egyptian goddess of Sais, the mysterious goddess whose veil in the old formula no mortal ever raised. 3 years later, a man named Paul Strubant took the whole thing apart. Working through the Royal Belgian Academy of Sciences in 1887, Strubant went through every reported observation, one at a time, and matched most of them to specific background stars that happened to lie near Venus on the specific night in question. Roed-Kjær's Copenhagen sightings resolved, in sequence, to Chi Orionis, then M Tauri, then 71 Orionis, then Nu Geminorum. Horrebow's final observation of 1768 resolved to Theta Librae. Short's object, Strubant concluded, had been a star somewhat fainter than 8th magnitude. That is what a disappearance looks like when the explanation is clean. It took 242 years from Fontana to Strubant, but the record was good enough to survive that long, and when someone finally sat down with it, the record answered. One observation held out longer than the rest. On the 13th of August, 1892, Edward Emerson Barnard recorded a 7th magnitude object near Venus, using the 36-inch refractor at Lick Observatory on Mount Hamilton in California, then the largest refracting telescope in the world. Barnard was one of the finest visual observers who has ever lived, and his object matched nothing in the Bonner Durchmusterung, which was the only whole-sky catalogue available at the time. That one stayed open for more than a century. It was finally closed in 2025 when Tim Hunter and Roger Saragioli worked through Barnard's own notebooks, including a page of graph paper he had glued into his logbook in March 1906, and showed that the star had been catalogued all along. Venus is not the only planet that good instruments have handed a phantom moon. On the 27th of March 1974, 2 days before Mariner 10's first flyby of Mercury, the spacecraft's ultraviolet spectrometer registered unexpected far ultraviolet radiation near the planet. One astronomer on the team said afterwards that it had no right to be there. Mercury has no atmosphere to speak of and should not produce that signal. The signal vanished on the 28th of March. Then, on the 31st, it came back, and this time it was clearly detached from Mercury, moving on its own at about 4 kilometers per second. Mercury's escape velocity is 4.25 kilometers per second, so this was something in the act of leaving. Managers at the Jet Propulsion Laboratory were called in on what one participant remembered as a hectic Friday, and there was a real internal argument about whether to announce the discovery of a moon of Mercury at the Saturday press conference. They did not, and it is as well they did not. The source turned out to be 31 Craterus, a spectroscopic binary star in the constellation Corvus, with a period of 2.9631 days, an apparent magnitude of 5.26, and a distance of about 1,931 light-years. The spacecraft had drifted its pointing across a background star. Mariner 10 flew past Mercury on the 29th of March 1974 at an altitude of roughly 740 kilometers and found no moon. Messenger, which orbited the planet from 2011 to 2015, confirmed it. That false alarm was not wasted, which is worth saying. It demonstrated that extreme ultraviolet light is not absorbed by the gas between the stars as thoroughly as everyone had assumed, a result reinforced later by the strong emission from the Gum Nebula at 540 angstroms across some 140 degrees of sky. The phantom taught something real about the transparency of the galaxy. There is one more thing worth knowing, which is that nobody is quite certain why Venus has no moon in the first place. Alex Alamy and David Stevenson proposed a model in which Venus did form one, in an early giant impact of the kind that made ours, and then a second impact, roughly 10 million years later, reversed the planet's spin, which caused the moon to spiral inward and be destroyed. The attraction of that model is that it explains two oddities at once, because Venus does rotate backwards, and it does so at a crawl, taking 243 Earth days to turn once. Venus does have a companion of a sort. 524522, Zuzve, found on the 11th of November, 2002, by Brian Skiff at the Lowell Observatory Near-Earth Object Search in Flagstaff, Arizona, is a quasi-satellite. It is about 236 meters across. It turns once every 13.5 hours, and it traces a looping path around Venus without ever being gravitationally bound to it. Its name is an accident. An artist making a poster of the solar system for children misread his own handwritten note, which said 2002 VE, and wrote Zoozve instead. Skiff put the misreading forward to the International Astronomical Union, and it was formally approved in February 2024. So that is the first entry, and it is the one where the record turned out to be better than the explanation. 30 observations. 20 named observers. Notebooks preserved for 3 centuries. And an explanation, when it finally came, that had been sitting inside the instruments the whole time. Hold on to that phrase, because we are going to need it again at the very end of this list, in a form that is a good deal less comfortable. The next entry on this list is the closest a comet has ever come to Earth. It was watched for 4 months, its orbit was solved by one of the best mathematicians alive, and the mathematics that should have told us where it went does not converge. Number 9. The comet that came closer than any other. On the night of the 14th of June 1770, at about 11 in the evening, Charles Messier was working at the Observatory of the Navy in the Hôtel de Cluny in Paris, and he found a comet near the constellation Scutum. His notes do not tell us much about the instrument. They say only that he was using the refractor for the night, which is the sort of phrase you write when you have used the same telescope so often that describing it feels unnecessary. 17 days later, on the 1st of July 1770, that comet passed 0.0151 astronomical units from the Earth. In more usable terms, that is about 2,260,000 kilometers, or roughly 6 times the distance to the Moon. It is the closest confirmed approach of a comet to the Earth in all of recorded history. And it has never been seen again by anyone, anywhere, since the 3rd of October of that same year. 6 lunar distances is a number that needs unpacking, because it sounds comfortable, and is not. The Moon takes 3 days to reach by rocket, and it is the only place beyond this planet that human beings have ever stood. This comet came within 6 of those, carrying a nucleus that modern reconstructions put at 10 kilometers across or more. 10 kilometers is larger than most mountains you can name. It passed at a distance that, in solar system terms, is essentially the doorstep, and it did so at a time when nobody on Earth had any concept that such a thing was possible. It looked spectacular. By the 24th of June, the coma had swollen to 27 arc-minutes across, which is very nearly the apparent width of the full Moon, and the comet had reached 2nd magnitude, about as bright as Polaris. At closest approach, Messier measured the coma at 2 degrees and 23 arc-minutes. That is roughly 4 full moons laid side by side in the sky. An English observer, whose name has not come down to us, recorded it crossing 42 degrees of sky in 24 hours, which is close to a quarter of the way from one horizon to the other in a single day, and described the nucleus as being as large as Jupiter, surrounded with a coma of silver light. Messier tracked it from the 14th of June to the 3rd of July. Then it was lost in the glare of the sun. He picked it up again from the 3rd of August, near Saturn, and followed it into the autumn. On the 3rd of October 1770, he observed it near Castor, and that was the last observation anyone has ever made of it. Charles Messier is the last human being to have seen this object. It was also recorded independently in Japan and in the Hejaz in the same month, by observers who had no idea the Paris observation existed. There is something worth pausing on in that observing site. The Hôtel de Cluny is a late medieval building in what is now the 5th arrondissement of Paris, and it still stands. It houses a museum of medieval art today. The Observatory of the Navy operated out of a tower attached to it, and that is where a man with a hand-guided refractor found the closest comet in recorded history, 16 days before it arrived. There was no warning system. There was no way to know it was coming. It was found because Messier was in the habit of sweeping the sky most clear nights, and it was found 17 days out because that is when it became bright enough to notice. Messier was very good at this. Louis XV nicknamed him the Ferret of Comets, and his surviving manuscript records 46 comets tracked between 1758 and 1808. He is remembered now for a catalogue of 110 nebulae and clusters that he compiled purely as a list of things that were not comets, so that he would stop wasting nights on them. The catalogue outlived the comets. That is its own small irony. The man whose name the comet actually carries never saw it. Anders Johann Lexell was born on the 24th of December, 1740, in Åbo, the town now called Turku, in what is now Finland. He worked at the Imperial Russian Academy of Sciences in St. Petersburg and became professor of astronomy there in 1771. He was a close collaborator of Leonhard Euler, the most prolific mathematician who has ever lived. He was present at Euler's death in 1783 and succeeded him as chair of mathematics. He died the following year, on the 11th of December, 1784, at the age of 43. On the 13th of October, 1778, Lexell presented his result to the St. Petersburg Academy, and it went directly against the assumption of the age. Comets, everyone believed, traveled on parabolas. They came in once from the depths, swung around the sun, and left forever. Lexell computed a closed ellipse with a period of 5.58 years. That was the shortest cometary period known to anyone at the time, by a wide margin. The orbit he derived had a perihelion of 0.6746 astronomical units, a semi-major axis of about 3.15, an aphelion near 5.62, an eccentricity of about 0.786, and an inclination of only 1.55 degrees. That last number is the interesting one. An inclination that small means the comet was lying almost perfectly flat, in the same plane as the planets, moving in the same direction, like a member of the family rather than a visitor. And then Lexell explained both halves of the mystery in a single stroke. A close encounter with Jupiter in 1767, he showed, had thrown the comet into the inner solar system. That is why nobody had ever seen it before 1770, despite the fact that it was bright enough to see with the naked eye. It had not been there. And a second encounter with Jupiter, due in 1779, would throw it somewhere else. Urbain Le Verrier later worked out that in 1779, the comet passed within about 3.5 Jupiter radii of the center of the planet. Io, the innermost of the 4 large Galilean moons, orbits at roughly 5.9 Jupiter radii. The comet went inside the orbit of Io. The 2 Jupiter encounters are worth holding side by side, because together they define the whole shape of the object's known life. Before 1767, it was somewhere in the outer solar system, on an orbit nobody has ever reconstructed, invisible from Earth. Jupiter reached out and pulled it inward, and for 12 years it ran on a 5.5-year loop through the inner system, which means it made roughly 2 circuits. On one of those 2 circuits, it happened to pass close to the Earth, and happened to do so at a moment when European astronomy had enough instruments and enough discipline to record it properly. Then Jupiter reached out a second time and took it away again. The entire observable history of this object is one 4-month window inside a 12-year visit, and the visit itself was an accident of one planet's gravity. Its disappearance became a formal scientific problem in the way that very few disappearances ever do. The Institut National in Paris offered prize competitions for an explanation. A first round was settled in 1794. Johann Karl Burckhardt won the renewed prize at a public session on the 5th of January, 1801, and the prize was a kilogram of gold. Burckhardt asked for Messier's original observing records and kept them for 2 years while he worked. His winning memoir appeared in 1806, and his answer was that after 1779, the comet's closest approach to the Sun had been pushed out to about 3.3 astronomical units, which would put it permanently beyond naked eye visibility. It was not destroyed. It was simply moved out of reach. Pierre-Simon Laplace used the encounter for something else entirely, and the something else is one of the more elegant pieces of reasoning in 18th century science. In 1805, in the fourth volume of his Celestial Mechanics, Laplace pointed out that the comet had passed close enough to the Earth that, if it had been massive, it would have measurably changed the length of our year. The year had not changed. From that absence of an effect, he set an upper limit on the comet's mass of 1/5000th of the mass of the Earth. He weighed an object he had never seen, using the fact that nothing happened. But the deepest result belongs to Leverrier, and it is the reason this entry sits where it does on the list. His foundational article on the problem is dated the 11th of November, 1844, with further work in 1848 and 1857. What he found is that the orbit after 1779 is hypersensitive. Tiny uncertainties in Messier's 1770 observations, entirely reasonable uncertainties for a man with a small refractor and a quadrant, expand once you propagate them forward through the Jupiter encounter to what Leverrier described as complete indetermination. Understand what that means. It does not mean the answer is difficult to compute. It means that impact with Jupiter and ejection from the solar system are both fully consistent with the same observations. The available data does not narrow the outcome at all. Modern orbit specialists call this the line of variation, and Leverrier's analysis is regarded as an early foreshadowing of chaos theory, more than a century before that phrase existed. The comet did not merely disappear. It took the possibility of knowing where it went with it. Modern work has reopened the question and made it stranger. In 2018, Quan-Ji Ye, Paul Wiegert, and Manto Hui reconstructed the orbit from Messier's 1770 measurements alone and propagated 10,000 orbital clones forward from 1770 to the year 2000. 98% of the clones remained gravitationally bound to the Sun, which means that ejection, the traditional answer, is now the less likely outcome. Roughly 40% of the bound clones ended up on orbits that bring them near the Earth. Their reconstruction also gives the comet a size, and the size is a problem. Absolute magnitude around 7. Active surface area between 50 and 1600 square kilometers. And a nucleus of 10 kilometers or more, which would make it one of the largest near-Earth comets ever recorded. An object like that, still active in the inner solar system, should have been picked up by survey telescopes decades ago. Comets that size are not subtle. The best candidate identification is an asteroid called 2010 JL33. It has an orbital similarity index of 0.087 against the reconstructed orbit, and only a 0.8% chance of matching that closely by pure coincidence. Its orbit was refined by the Goldstone radar in 2010. It is 1.8 kilometers across, with an albedo of 0.047, turning once every 9.41 hours. And 1.8 kilometers is not 10 kilometers. The paper does not resolve the discrepancy. The authors tested 10 million combinations of non-gravitational parameters, the small pushes that outgassing gives a comet, and could not force a precise match. In their own words, the linkage has not been successfully accomplished, and the search is fraught with local minima and sharp gradients. There is one more absence inside this absence, and it is quietly the strangest part. Their modeling suggests that about half the plausible orbits should produce a meteor shower at the Earth, because a comet of that size passing that close leaves debris. No meteor shower has ever been unambiguously linked to Lexell's comet. Not one. For scale, it is worth knowing what the competition looks like. Halley's comet passed 0.0334 astronomical units from Earth on the 10th of April, 837 of the Common Era, which is about 4.9 million kilometers. It was as bright as Venus, with a tail stretching across more than 90 degrees of sky, and it is recorded in Chinese and European chronicles alike. 55P Tempel-Tuttle, the comet that supplies the Leonid meteor shower, passed 0.0229 astronomical units on the 26th of October, 1366. And in living memory, the comet Ira-Saraki-Alcock passed 0.031 astronomical units on the 11th of May 1983 at magnitude 1.5, with a coma about 3 degrees across, 6 full moons wide. That one was found 3 separate ways within days, by the Iris satellite, by the amateur astronomer Genichi Araki in Japan, and by the amateur George Alcock in the United Kingdom. There is one technicality that comet historians argue about. A fragment designated P/1999J6, found by the Soho Solar Observatory, passed 0.012 astronomical units from Earth on the 12th of June 1999, which is closer than Lexell's comet managed. But that object was at most 48 meters across and completely invisible to the naked eye. It was only detected at all because a spacecraft that stares at the sun happened to catch it. Some record books credit it. The value is described elsewhere as highly uncertain, and for anything a person could actually have stood outside and watched, Lexell's comet holds the record. Statistically, a comet passes within 14.5 million kilometers of Earth, roughly every 30 to 40 years, and within 8 million kilometers, roughly every 80 to 90 years. Lexell's comet came within 2.25 million. Halley next passes at 13.8 million kilometers on the 7th of May, 2134, which is close enough that a fair number of people alive today have grandchildren who will see it. The formal designation of Lexell's comet is D/1770L1. The letter D at the front is not decorative. In cometary nomenclature, D stands for a comet that has disappeared or that is considered to no longer exist. It is astronomy's official way of writing down a loss, and there are only a handful of objects that carry it. And there is one last thing that ought to be said about this entry, because it complicates the idea of loss. Lexell's work on this comet is regarded by historians of the International Astronomical Union as the beginning of modern orbit determination as a discipline. The methods that now let us predict asteroid approaches decades in advance were developed, in large part, by people trying to work out where one comet went. The disappearance created the field that studies disappearances. A comet can be lost and stay lost. That is more or less the natural condition of comets, and Lexell's is the grandest example of it. But the next object on this list was lost, and then it came back. Not as a comet. Number 8, the comet that came back as rain. The third comet ever confirmed to be periodic was called Biela's comet, and it did something in front of witnesses that no comet had ever been seen to do. It split in half. Then it came back, still in 2 pieces, further apart. Then it did not come back at all. And then, on a November night in 1872, in the year when the Earth crossed the point in space where the comet should have been, the sky over Europe filled with meteors. Start with the number that gives this story its edge. At the 1832 epoch, the minimum distance between this comet's orbit and the Earth's orbit was 0.0005 astronomical units. That is about 75,000 kilometers, which is a fifth of the way to the Moon. It was the only comet then known whose orbital path actually crossed our own. Not came near. Crossed. The comet was found 3 separate times before anyone realized it was one object. The first recorded sighting was on the 8th of March, 1772, by Jacques Lebac's Montaigne at Limoges in France, which is the same Montaigne who had reported a moon of Venus 11 years earlier, and who is therefore a small recurring character in this list. Charles Messier picked it up independently shortly afterwards. That apparition stayed just below naked eye visibility, at about 7th magnitude, and was followed for 29 days before it faded out. It returned on the 10th of November 1805, discovered by Jean-Louis Pons at Marseille, and followed for about 36 days. That apparition was much better. Around the 9th of December 1805, it passed 0.0366 astronomical units from Earth, 5.48 million kilometers, which is its closest verified approach, and it reached 4th magnitude or brighter, easily visible to the naked eye. Carl Friedrich Gauss and Friedrich Bessel both attempted orbits for it in 1806. Gauss and Heinrich Olbers suspected that the 1772 and 1805 comets were the same body and could not prove it. The proof came from an army officer. Wilhelm von Biela was an Austrian officer, later a major, stationed at the fortress town of Josefstadt in Bohemia, which is the modern Czech town of Jaromír. The fortress itself was built between 1780 and 1787 and still stands. On the 27th of February 1826, Biela rediscovered the comet in the constellation Aries and computed its orbit. That apparition was followed for 72 days, more than twice as long as either previous one, and 72 days is enough baseline to pin down a period. Biela derived 6.6 years. That made it the third comet in history confirmed to be periodic, after Halley and after Encke. Jean-Félix Adolphe Gambart at Marseille independently connected the 1826 apparition to 1805 and supplied the first mathematical proof. Their letters appeared in the same issue of Astronomische Nachrichten, and for years in France, the object was known as Gambart's Comet. Thomas Clausen at Altona independently computed 6 years and 3/4 at about the same time. 3 men, 1 comet, and 1 name that happened to stick. Then came the panic of 1832, which is worth telling properly because it is one of the earliest examples of a story that is now very familiar. Olbers predicted, and Marie-Charles Damoiseau refined with the perturbations of the planets included, that on the 29th of October 1832, the comet would cross the plane of the Earth's orbit at almost exactly the point the Earth occupies. That is a true statement, and the European press printed it. What the press left out was the timing. The Earth would not arrive at that point until the 30th of November, about a month later. At the moment of the comet's crossing, the two bodies would be roughly 0.55 astronomical units apart, which is 82 million kilometers. The comet was going to pass through a doorway that we would walk through 4 weeks after it had gone. François Arago published a calming tract, in which he put the probability of a collision at 1 in 281 million. He then rather undercut his own work by conceding that the gases in a comet's tail might, in some circumstances, cause the death of all animals or produce epidemics. Public anxiety about comets was not invented recently, and neither was the difficulty of reassuring anyone about anything. The comet came back on schedule. Francesco De Vico, director of the Vatican Observatory in Rome, recovered it on the 26th of November, 1845. And then, in the middle of January 1846, Matthew Fontaine Maury at the United States Naval Observatory in Washington noted something beside it. a companion object, 1 arc-minute to the north. Edward Herrick and Francis Bradley observed the same thing at Yale within days. The comet had 2 nuclei. Through the 1846 apparition, the 2 components alternated in brightness. First one was brighter, then the other, then the first again, over weeks, as though they were trading something back and forth. They developed parallel tails, and observers recorded what several of them described as an archway of cometary matter arching between the 2 nuclei, a bridge of material connecting the halves. According to George Cronk's catalogue of cometography, the pair remained about 1.6 million miles apart for the entire apparition. Perihelion for that return came on the 11th of February, 1846. At the 1852 return, the 2 halves were recovered separately, as 2 comets. Angelo Secchi found Comet A in Rome on the 26th of August, 1852. Comet B was relocated on the 15th and 16th of September. By then, the astronomer Hubbard calculated the separation at about 1,750,000 miles, which is roughly 2.8 million kilometers, or about 7 times the distance from the Earth to the Moon. In 6 years, the 2 halves had drifted 7 moon distances apart. Otto Wilhelm Struve made the last detection of Comet A on the 26th of September, 1852, and of Comet B on the 29th of September, 1852. That is the last time any human being saw Biela's comet in any form. The 1865–66 return should have been easy. The geometry was excellent. The comet was due to pass 0.22 astronomical units from Earth in late February 1866, and every serious observer in the Northern Hemisphere was looking for it. Nothing. Charles Talmage and James Buckingham reported possible sightings in November 1865, working from ephemerides supplied by John Russell Hind, and Hind himself judged them unlikely to be real. In 1872 there was again no trace, and the comet was formally declared lost. Here is the detail that makes the 1872 connection so persuasive, and it is a detail almost every retelling leaves out. The Andromedid meteor shower was not new. The earliest known appearance of the stream is the 6th of December, 1741, recorded from St. Petersburg, and there were strong showers in 1798, in 1825, in 1830, in 1838, and in 1847. The stream predates the observed breakup by more than a century, which means the comet had been shedding material along its path for generations before anyone watched it come apart, and that what happened in the 1840s was not the beginning of the disintegration. It was the part of the disintegration that happened to be visible. And then, on the 27th of November, 1872, the Earth crossed the comet's orbital node, and the Andromedids arrived. The rate estimates from that night vary, and it is worth being honest about why. 19th century observers counted differently, some reporting what a single pair of eyes could see, and others estimating what was falling across the whole visible sky. The commonly cited figure is around 3,000 meteors per hour, with 4 hours above 1,000 per hour. Some modern summaries put the peak as high as 10,000. P. F. Denza at Moncalieri in Italy counted 33,400 meteors in 6.5 hours. S. J. Perry at Stonyhurst Observatory estimated a whole sky peak of about 100 meteors a minute. Edward Joseph Lowe in England estimated at least 58,600 visible meteors between 10 to 6 and 10:30 in the evening. Johann Friedrich Julius Schmidt, watching from Athens, described faint meteors of 5th and 6th magnitude with broad smoke-like trains, predominantly orange and red. That night also produced one of the strangest telegrams in the history of the science. Ernst Friedrich Wilhelm Klinkerfues at Göttingen wired Norman Pogson at the Madras Observatory in India. The message, in full, read, "Biela touched Earth on the 27th. Search near Theta Centauri." Pogson looked. And on the 3rd and 4th of December 1872, he recorded a cometary object, which was catalogued as X/1872X1 and is still sometimes called Pogson's Comet. Whether it was a piece of Biela has been argued about ever since. Lieutenant Colonel George Lyon Tupman flagged inconsistencies in position and timing at the time, and Patrick Moore, much later, called the identification inconceivable. It is one of those threads that never quite resolves. 13 years later, the shower came back, and it came back as one of the greatest meteor storms ever recorded. Picture the night of the 27th of November, 1885, from a field outside Marseille. It is cold and clear. The radiant sits high in the north, in Cassiopeia, and the meteors are coming from that point at a rate that stops making sense within about 90 seconds of you starting to count. They are not the sharp white streaks of a fast shower. These come in slowly, at 16 kilometers per second, orange and reddish, leaving broad trains behind them that hang in the air like smoke and drift before they fade. There are 20 a second. You cannot look at all of them. You cannot look at most of them. Whichever direction you turn, several are falling in the corner of your eye, and the corner of your eye is where you keep noticing more. And every single streak is a fragment of an object that 4 men, 39 years earlier, watched split in half through their telescopes, and then watched drift apart, and then watched fail to return. Somewhere else in Europe that same night, in Prague, a man named Ladislaus Weineck has a photographic plate open at the sky, and he catches one. 7 millimeters of trail on a glass plate. It is the first photograph of a meteor ever taken. The authoritative rate for that storm is 75,000 per hour, computed by Hubert Newton in the American Journal of Science in June 1886, using counts from Marseille Observatory at 233 meteors a minute from a single observer, from Palermo at 213 a minute over 5 minutes, and from Beirut and Moncalieri. Contemporary Chinese records from that night say that the stars fell like rain. In Burma, the display was read as an omen preceding the fall of the Konbaung dynasty to British conquest, which happened within days. There is also a stubborn footnote. An iron meteorite, a medium octahedrite weighing 4.656 kilograms, fell at Mazapil in Zacatecas, Mexico, on the very night of the 1885 storm. From about 1886 through to the 1950s, that coincidence was cited as proof that comets contain solid iron. It has been rejected since then. The timing appears to have been a genuine coincidence, and cometary material does not survive as iron meteorites. But for 70 years it was in the textbooks. Then the shower faded, and you can almost watch the decay in the numbers. At the maximum of the 24th of November, 1892, Daniel Kirkwood counted 150 meteors in 30 minutes, and Charles Perrine counted 1,013 in an hour and 18 minutes. On the 24th of November, 1899, 100 per hour. On the 21st of November, 1904, 20 per hour. Meanwhile, Jupiter's gravity was steadily dragging the whole stream sideways. The date of maximum moved from mid-December in 1798 and 1838, to late November in 1872 and 1885, to mid-November by the early 20th century, and the radiant drifted about 20 degrees south of where it had been. There is one story attached to this comet that should be set aside firmly, because it circulates and it is not true. The claim that fragments of Biela started the Great Chicago Fire originates with a book called Ragnarok, published by Ignatius Donnelly in 1883, and it was revived in a popular book in 1985. It does not survive contact with the dates. The Chicago Fire and the Peshtigo Fire in Wisconsin that killed far more people the same night both happened on the 8th of October, 1871, which is more than a year before the 1872 storm. Meteorites arrive cold rather than hot, having spent only seconds in the atmosphere and having shed their outer layer in the process. There is no credible recorded case of a meteorite starting a fire, and the blue flames witnesses described have been attributed by historians to burning natural gas from ruptured street mains. It is a good story, and it is not what happened. For the record, the orbital elements as they stood at the 1852 epoch, a perihelion of 0.8606 astronomical units, an aphelion of 6.19, an eccentricity of 0.7559, an inclination of 12.55 degrees, and a period of 6.619 years. Those numbers are the last measurements anyone will ever take of this object as a comet. Everything after them is inference from dust. By the middle of the 20th century, the Andromedids were effectively a dead shower. A handful of meteors an hour, on a good year, from a stream nobody expected anything from. And then, radar found something nobody predicted. Between the 3rd and the 5th of December 2011, the Canadian Meteor Orbit Radar detected an Andromedan outburst with a zenithal hourly rate of about 50, the strongest return in more than a century, with roughly 122 probable orbits measured and a radiant matching the classical position in Cassiopeia. The analysis, by Paul Vigott, Peter Brown, Robert Werrick, and Daniel Wong at Western Ontario, traced the material back to its source. It did not come from the famous breakup of 1846. It came from the comet's perihelion passage of 1649. On the 28th of November 2021, there was a stronger outburst still. More than 100 faint meteors an hour, peaking at 18 minutes past 5 in the morning Universal Time, the strongest Andromedan return that radar has ever recorded, traced to a dust trail laid down around 1655. Video networks triangulated 122 of them, at an average magnitude of plus 3.9, which is faint enough that most would go unnoticed by a person standing outside. The meteoroids have a mean mass of about 5/10 millionths of a kilogram. Grains 0.5 millimeter across. The modeling predicts further outbursts, each roughly 4 times stronger than 2011. So the comet is still arriving. Not the pieces that split in 1846, which are somewhere else entirely, or nowhere at all, but material this object shed on passages that happened before Isaac Newton was born, drifting for 3.5 centuries and hitting the top of our atmosphere at 16 kilometers a second, in grains you would need a microscope to find. That comet at least left something behind, which puts it in a small minority on this list. The next entry is an object we never saw at all. Not once. Everything anyone knows about it comes from a mark it made on something else. Number 7. The Moonlet at the edge of Saturn's rings. On the 15th of April 2013, the narrow-angle camera aboard the Cassini spacecraft photographed a bright arc at the very outer edge of Saturn's A-ring. The arc was about 1,200 kilometers long, about 10 kilometers wide, and roughly 20% brighter than the ring material around it. In the raw images, it is unmistakable, a pale streak lying along the ring's outer boundary like a scratch on glass. The arc is not the object. The arc is what the object was doing to everything around it. Carl Murray, professor of astronomy at Queen Mary University of London, was the first to notice it, and he named it Peggy after his mother-in-law, because the day he found it in the data was her birthday. On seeing it, he said, "You couldn't miss it." It was a very bright, kind of extended object, somewhere near the edge of the ring. That is how this entry begins, and the reason it belongs on this list is that Peggy itself has never been photographed. Not once, by anything, ever. Everything anyone knows about it is inferred from the shape and brightness of the disturbance it leaves behind, and by the time Cassini's mission ended, even the disturbance had stopped being reliable. The object sits at an orbital radius of about 136,775 kilometers from Saturn's center. That is the outermost edge of the A ring, which is to say, the outer shore of the entire main ring system. Beyond it, there is a gap of tens of thousands of kilometers before you reach the faint and diffuse outer rings. Peggy is estimated at no more than about half a mile across, which is under a kilometer. That is small enough that Cassini's cameras could never resolve it directly at any distance the spacecraft ever managed. To understand why an object that size can leave a 1,200-kilometer mark, it helps to know what Saturn's rings actually are. They are more than 95% water ice by mass, which is why they are so bright, and they are spread into a sheet that is typically about 10 meters thick. 10 meters. That is the height of a 3-story building, spread across a disk 280,000 kilometers wide. If you scaled the main rings down to the width of a football pitch, they would be very much thinner than the paper this script is written on. Nothing in ordinary experience is that flat. The total mass is equally counterintuitive. Cassini measured it during the grand finale, by flying between the planet and the rings, and letting Saturn's gravity and the ring's gravity pull on the spacecraft in slightly different directions, while a continuous radio link ran back to Earth. The answer came out at 1.54 times 10 to the 19th kilograms. Mimas, the smallest of Saturn's round moons, the one with the enormous crater that makes it look like a face, has a mass of about 3.75 times 10 to the 19th kilograms. Every ring around Saturn, all of them together, weighs less than half of one small moon. Inside that thin sheet, objects a few hundred meters to a kilometer across carve visible structures called propellers. The name describes the shape. The Moonlet's gravity pushes ring particles aside on both sides, ahead on one side and behind on the other, producing a double-armed streak without ever clearing a complete gap. Matthew Tiscareno and colleagues at Cornell found the first 4 of them in Cassini data in 2006, and the larger ones were named after aviation pioneers: Blériot, Earhart, Santos-Dumont, Sikorsky, Post, and Quimby. 3 propeller belts between 127,000 and 132,000 kilometers are estimated to contain 7,000 to 8,000 moonlets, larger than 150 meters, and the total population in the 100-meter class may run to 10 million objects. Blériot is the largest known, with a central moonlet about 860 meters across. It was tracked in more than 100 separate Cassini images, plus 1 ultraviolet observation, which prompted NASA to describe it as a veritable Forrest Gump for the number of pictures it kept turning up in. Blériot is roughly 60% wider than the moonlet at the heart of Santos-Dumont, which makes it about 4 times more massive. The giant propellers kick ring material as much as half a kilometer above and below the ring plane, out of a sheet 10 meters thick. Proportionally, that is like a pebble dropped in a puddle throwing up a splash 50 times the depth of the water. There is one more piece of structure worth knowing about, because it explains why the outer edge of the A-ring is such a violent neighborhood. That edge does not simply fade out. It is held in place, sharply, by a gravitational resonance with the moon Janus. Janus orbits at a distance where it completes 6 circuits of Saturn in the time a ring particle at the edge completes 7, and that 7-to-6 ratio means the Moon tugs on the same particles in the same direction over and over, in step, until they are pushed back into line. The resonance sits only about 4 kilometers inside the ring's edge. The result is a 7-lobed standing pattern of radial distortion, with an amplitude of about 12.8 kilometers, rotating around the planet at the speed of Janus. So an object sitting at that edge is not sitting somewhere calm. It is sitting inside a repeating gravitational squeeze that flexes the ring boundary in and out by more than 10 kilometers, 7 times per orbit, forever. For a loosely bound pile of ice a few hundred meters across, that is not a gentle place to try to hold yourself together. Just inside are 2 gaps that show what a slightly larger object can do. The Encke gap is about 320 kilometers wide, centered at 133,581 kilometers, and it is cleared by the Moon Pan, which is about 26 kilometers across. The Keeler gap is only about 42 kilometers wide, at roughly 136,505 kilometers, cleared by Daphnis, which is about 7 kilometers across. Peggy is smaller than either of those shepherds by a wide margin. It could not clear a gap. All it could do was leave a smear. So the ring is full of small bodies making marks. What made Peggy different was where it was sitting. It was not buried in the middle of the ring, in the propeller belts, with material on all sides. It was at the outer boundary. It was at the exact place where a moonlet stops being ring material and starts being a moon. That is why the story got the attention it did, and why Murray's sentence went around the world in April 2014. We may be looking at the act of birth, where this object is just leaving the rings and heading off to be a moon. The idea behind that is well-founded. Saturn's small inner moons are thought to have formed exactly this way, accreting at the ring edge out of ring material and then migrating outward under the influence of the planet's tides. Pan, in the Encke gap, is about 26 kilometers across. Daphnis, in the Keeler gap, is about 7. Those 2 are shepherds. They are inside the ring system, and they clear their gaps. Further out sit Atlas and Prometheus and Pandora and Janus and Epimetheus. All of them, in the standard picture, came from the ring. Watching one form would be watching the last stages of a process that made all of them, and depending on how much material the rings have left, it might be the last moon Saturn will ever make. It is worth pausing on what watching that would actually mean, because it is unusual. Almost everything in planetary science is reconstructed after the fact. We work out how the moon formed by looking at rocks 4 billion years old. We work out how planets accrete by looking at other stars' disks and building models. Nobody expects to see the process happen. A moon forming at the edge of Saturn's rings, in real time, photographed while it happens, would be one of a handful of events in the history of the field where a formation process was caught in the act rather than deduced. That is the reason a half-mile lump of ice got a name and a press release. The peer-reviewed paper was considerably more careful than the press coverage. It appeared in the journal Icarus in 2014, written by Murray with Nick Cooper, Gareth Williams, and Nick Atree at Queen Mary, and Jonathan Boyer at the Jet Propulsion Laboratory. It describes, in its own words, an unresolved, evolving, sub-kilometer radius object. And it notes that the changing orbit shows evidence of a possible disruption in early 2013. Breakup was in the paper from the very beginning, sitting quietly in the abstract while the headlines talked about birth. The follow-up data went that way. Retroactive searches found the disturbance in Cassini images going back to at least May 2012, a year before the official discovery frame. Then, Images from the middle of 2013 showed two smears rather than one, moving independently of each other. Peggy had fractured. By late 2013, one of the two smears had vanished entirely, and the one that remained had dimmed and was migrating inward, deeper into the ring, rather than outward toward freedom. In 2014, the object appeared much dimmer than it had the year before. At the American Geophysical Union meeting in December 2014, Matthew Tiscareno gave the assessment that the situation was not as clear as you would like. In January 2015, Nadia Drake published a piece in National Geographic under the title "The Not-So-Sad Story of Peggy," which reframed the whole thing. This might be a moon dying rather than a moon being born. And then Murray put the sharpest version of the problem himself. It may be, he said, that we saw the split of the object itself. That's why it was so bright. Follow that through. Breaking a small icy body apart produces dust. Dust has an enormous amount of surface area for its mass, and it scatters sunlight extremely efficiently. The brightness that made Peggy detectable in the first place may have been the debris cloud of its own destruction. We may only have been able to see it because it was coming apart. The last few years of the mission complicated it further rather than resolving it. In 2015 and 2016, the object reappeared in Cassini data, not entirely intact, alongside a second nearby chunk that the team informally called Peggy B. At the fall meeting of the American Geophysical Union on the 14th of December 2016, Murray suggested that Peggy had collided with an unknown object in early 2015, a collision that pushed it deeper into the A-ring, spawned Peggy B, and produced a co-orbiting cloud of icy debris. He added a comment that circles the whole item back on itself, noting that probably the discovery of Peggy itself was facilitated by a collision which produced a large glow. On the 13th of January 2017, the BBC ran a story with the headline, "To see finally the face of Peggy." Cassini's ring-grazing orbits and the grand finale that followed were expected to deliver the closest look that anyone would ever get at this object, and high-resolution observations of the A-ring in Peggy's vicinity were obtained. No direct image of Peggy was ever produced. On the 15th of September 2017, Cassini entered Saturn's atmosphere at roughly 34,000 kilometers an hour and was destroyed. It had been in orbit since the 1st of July 2004, after a launch from Cape Canaveral on the 15th of October 1997 on a Titan 4B rocket. The grand finale consisted of 22 orbits, threading the gap between the planet and the rings at altitudes of roughly 1,600 to 4,000 kilometers above the cloud tops, beginning on the 26th of April 2017. In its very last ring images, taken the day before the final plunge, Cassini photographed all 6 of the tracked propeller moonlets. The aviators got a farewell. Peggy did not. There is a small human detail attached to the discovery that is worth keeping. A visiting secondary school student named Jenya Maurice from Ardingly College assisted with the work at Queen Mary through a competition the department ran called Cassini Scientist for a Day. Which means that among the people who worked on the identification of the last moon Saturn may ever have made was a teenager on a school placement. And for a sense of how much of Saturn's system remains uncounted, on the 11th of March 2025, the Minor Planet Center added 128 new Saturnian moons in a single announcement, bringing the confirmed total to 274. That is more moons than every other planet in the solar system combined. They were found with the Canada-France-Hawaii telescope, observing between 2019 and 2021 and revisited in 2023, and most of them are irregular captured bodies a few kilometers across in distant orbits. Peggy is not among them, and could not be. It is far too small and far too close in. Saturn is a planet where we are still finding moons 100 at a time, and the one we watched most closely is the one we cannot account for. Murray's closing assessment was straightforward. It may be, he said, that the original Peggy has left the rings, in which case we'll be hard-pressed to see it again. Which is where it stands. Peggy either escaped the ring system as a new moon, or was destroyed and dispersed into material too fine to notice, or is still there and simply quiet. There is no mission planned that could tell the difference. The Cassini orbiter was the only instrument ever built that could see a disturbance of that size at that distance, and it is now part of Saturn. There is a wider question sitting underneath this one, and it is unresolved in a way that changes what Peggy means. The low ring mass measured during the grand finale was read by Luciano Yies and colleagues in 2019 as implying that the rings formed only 10 to 100 million years ago, which is startlingly recent against Saturn's 4.5 billion years. Sascha Kempf at the University of Colorado, using the final measurements from Cassini's cosmic dust analyzer, put the exposure time at 100 to 400 million years, based on how much dark micrometeorite material the ice has picked up. But that reading has been challenged. Gregorio Ricerchi and Aurelian Crida have argued that exposure age is not the same thing as formation age, and their models show ring mass converging toward the value Cassini measured after about 4 billion years, regardless of what it started with. An ancient origin remains entirely compatible with the data. This is genuinely unsettled, and it should not be presented as decided in either direction. It matters here because it decides what kind of thing Peggy was. If the rings are young, then Peggy was one of the last objects a very short-lived structure ever made, and we happened to be watching in the narrow window when that was still possible. If the rings are old, then Peggy was routine, and objects like it have been forming and breaking apart at that edge continuously since long before the first cell divided on Earth, and we simply had a camera there for 13 years out of 4 billion. Either way, the evidence is the same, and the evidence is a gap. 1,200 kilometers of ring material pushed aside by something we never saw. We know it was there because of what was not there around it. Something clearly did the emptying. Peggy was a half-mile object we could not photograph, and its absence is measured in kilometers of disturbed ice. The next entry on this list is a disappearance large enough to build planets out of. And it happened in under 2 years. Number 6, the disk that lost, a solar system's worth of dust. There is a star in the constellation Centaurus with a catalogue designation rather than a name. It is listed as TYC 824126521, which is a Tycho catalogue number and nothing more. It is a K-type star, cooler and smaller than the Sun, about 10 million years old, and somewhere between 390 and 450 light-years away depending on which measurement you take. The older press figure is 450. The Gaia astrometry mission gives 120.9 parsecs, which works out to 394. Both numbers circulate, and for our purposes it does not matter much. It is close, in galactic terms. It is in our neighborhood. For at least 25 years, that star was surrounded by a bright, warm, dusty disk. Then, between 2008 and 2010, the infrared brightness of that disk fell by a factor of at least 30. Roughly 2/3 of it was gone by January 2009. Essentially, all of it was gone by 2010. And the star did not change. Its visible brightness held perfectly steady throughout. Its X-ray output has been constant since 1991. Nothing happened to the star. Everything happened to the dust. Carl Mellis, who led the work, put it about as plainly as it can be put. Enough dust, he said, to fill an inner solar system, and it really is gone. His colleague Benjamin Zuckerman, who has spent a career on debris disks, gave the comparison that makes it land. "It's as if," he said, "the rings around Saturn had disappeared." Except that this disk was both considerably larger than Saturn's rings and far more massive. Let us establish the size of the thing that went missing, because the number is what makes this entry an anchor. At its maximum, the infrared excess from this disk amounted to 11% of the star's total output. That is what an infrared excess is: light from the star, absorbed by dust, re-radiated at longer wavelengths. 11% means the disk was intercepting and re-emitting roughly 1/9 of every photon the star produced. That requires a lot of surface area, which requires a lot of dust. The temperature tells you where it was. The dust was radiating at a fiducial temperature around 450 Kelvin, with the possibility that some of it ran as hot as 800. 450 Kelvin is 177 degrees Celsius, which is roughly the temperature of a domestic oven set for baking bread. Dust at that temperature, around a star like this one, sits about 0.6 astronomical units out. Translate that into our own system. It is the zone between the orbit of Mercury and the orbit of Venus. Zuckerman's framing was that the disk would have extended from the Sun halfway out to Earth, near the orbit of Mercury. And this is not decorative material. Warm dust in that particular zone around a 10-million-year-old star has a specific meaning in the field. It is post-collisional debris. It is the wreckage produced when the forming bodies of a young planetary system smash into one another, which is not an accident of the process, but the process itself. Rocky planets are built by collisions, and collisions make dust. The material around this star was, in the most literal sense available, planet-building material caught in the act. One more thing about the star, because it becomes important later. We know its age with unusual confidence, and the reason is lithium. Lithium is a fragile element. It is destroyed by nuclear reactions in the interiors of stars, and once a young star's convection has carried its lithium down to where it can be burned, it never comes back. So the presence of a lithium absorption line in a star's spectrum is a clock that only runs while the star is young. This star has one. Its 10-million-year age is not an estimate from a model. It is written in the spectrum. I want to slow down here and put you inside it, because the numbers are abstract and the situation is not. You are standing at 0.6 astronomical units from this star, in the year 2007. The star is a hot orange disk, larger in the sky than our Sun looks from Earth. Around you, in every direction, the sky is not black. It is a dull, glowing haze, thick enough that the stars beyond it are dimmed and reddened, and it is warm. 450 Kelvin, radiating from all sides. There is no wind in it. It is not moving in any way you could perceive. It is simply there, a vast fog of rock powder circling a young star, and if you could stay long enough, you would watch it settle over tens of millions of years into worlds. Now hold that position and let 2 years pass. Nothing happens. That is the important part. There is no flash. There is no shock front sweeping through. There is no wind that rises. The star does not flare, does not pulse, does not so much as flicker. The haze simply thins. The reddening lessens. The background stars come back one by one, and the warmth drops away. And at the end of 2 years, you are standing at 0.6 astronomical units from a perfectly ordinary young star, with nothing between you and the rest of the universe. The material that was going to be a planet is not there, and there is no evidence of where it went. There is one more oddity in that picture. and it will matter when we start eliminating explanations. This star is extraordinarily active in X-rays. The ratio of its X-ray output to its total output, expressed as a logarithm, comes out at -2.8. The theoretical saturation value, the ceiling that stars of this kind cannot exceed, is -3. Typical stars that host debris disks run between -4.5 and -7. This star is running roughly 100 times more X-ray active than a normal disk host, right at the physical limit, and it has been doing so consistently for the entire period of observation. Whatever killed the disk, it was not a change in the star, because the star has been doing the same extreme thing throughout. The observational record on this is unusually good, which is what makes it a problem rather than a curiosity. The infrared excess was first detected by IRAS, the Infrared Astronomical Satellite, in 1983. IRAS was a joint mission of NASA, the Netherlands, and the United Kingdom, the first observatory to survey the entire sky in the infrared, and it flew for 10 months before its coolant ran out. It found this star's excess and catalogued it. And thereafter, the excess appeared in every observation, across the 8 to 25 micron range for a quarter of a century. In the words of the Jet Propulsion Laboratory's summary in 2012, it continued to glow brightly for 25 years. Mellis and colleagues have 10 micron measurements for 2006, for May 2008, and for January 2009, with the flux peaking in 2008. The first strong sign that something had gone wrong came from images taken by WISE, the Wide Field Infrared Survey Explorer, in January 2010. By then, the 10-micron flux stood at 12.6 millianskys. Here is why that number is the whole story. The expected emission from the bare surface of the star alone, with no disk at all, is about 11 millijanskys. 12.6 is 11 plus almost nothing. There was essentially nothing left above the photosphere. They checked, repeatedly, with different instruments, because a result like that is the kind of thing that is usually an instrumental error. A Gemini South image taken on the 1st of May 2012, using the thermal region camera spectrograph at Cerro Pachón in Chile, confirmed that the warm dust had by then been gone for 2.5 years, and that observation arrived while the paper was being accepted. A Subaru observation on the 19th of June 2013 was a non-detection. And a very large telescope observation with the Vizier instrument on the 16th and 17th of February 2016 measured 11 plus or minus 2 millianskys. Bare photosphere to within the error bars. As of the last published measurement, the disk had not come back. It is worth listing the instruments involved, because the roll call is itself an argument. Over the course of the campaign, this one star was observed by IRAS, by Spitzer, by WISE, by the Thermal Region Camera Spectrograph on Gemini South, by COMET on Subaru, by Vizier on the Very Large Telescope, by amber interferometry linking the Very Large Telescope's units, by aperture masking with NACO, by the WIFES spectrograph on the Siding Spring 2.3 meter, by the Goodman spectrograph on the 4.1 meter SOAR telescope, by the Rosat All-Sky Survey, by XMM Newton, and by Chandra. Ground-based and orbital, optical and infrared and X-ray, across 4 decades and 3 continents. It is not a marginal result from one instrument having a bad night. There is also a small survivor worth noting. WISE detected a residual excess near 20 microns after the warm disk vanished, which suggests that a colder outer disk, further from the star, may have survived the event that destroyed the inner one. Whatever happened was surgical. It took the warm material at half an astronomical unit and left the cold material further out alone. The paper appeared in Nature on the 5th of July 2012 under the title Rapid Disappearance of a Warm, Dusty Circumstellar Disk by by Carl Mellis, then a postdoctoral scholar at the University of California, San Diego, with Benjamin Zuckerman at UCLA and Joseph Ree. Its abstract contains one of the flatter admissions you will find in a modern astronomy paper. Such a phase of rapid ejector evolution, it says, has not been previously predicted or observed, and no currently available physical model satisfactorily explains the observations. Now the timescale problem, which is why this sits where it does on the countdown. Disks around young stars come in two broad kinds. The primordial kind, gas-rich and left over directly from the cloud the star formed out of, lasts a few million years before the gas is dispersed. The debris kind, which is what this was, is dustier and later, and is continuously replenished by collisions among the leftover bodies, and it lasts hundreds of millions of years to billions of years. That is not a guess. It is the baseline from every survey ever conducted across thousands of stars. This one changed in under 2 years. Set those against each other. Against the debris disk baseline, the discrepancy is roughly 8 to 9 orders of magnitude. Numbers that large stop meaning anything, so here is a version you can hold. If the expected lifetime of the disk were a human lifetime, 80 years, then the observed change took about 2.5 seconds. That is the ratio. Zuckerman, who had by then been working on these objects for decades, said, "This disappearance is remarkably fast even on a human timescale, much less an astronomical scale." And, more revealingly, he said it was so bizarre and so quick that initially he figured their observations must simply be wrong in some strange way. Mellis's version, a perplexing thing about this discovery, is that we don't have a satisfactory explanation to address what happened around this star. The follow-up work went looking for one. It was led by Hans Moritz Günther at the Massachusetts Institute of Technology, with Adam Krauss and Mellis, and it appeared in Astronomy and Astrophysics in February 2017 under a title that gives away the ending, The Case of the Disappearing Disk, No Smoking Gun Yet. What that paper mostly does is kill things. Obscuration was the first candidate, and it is the obvious one. Something drifted in front and blocked the dust from view. Rejected. The star's optical brightness never changed. The fitted hydrogen column density along the line of sight comes out at 0, and the visual extinction is consistent with 0. There is nothing in the way. There has never been anything in the way. A stellar flare, evaporating the dust, was the second. Young stars flare enormously. This one is unusually active. Rejected, and decisively. The energy required to evaporate that much material is around 10 to the 39th ergs. That is more than any stellar flare ever observed by anyone on any star. Data from the Kepler mission show flare energies saturating near 2 times 10 to the 37th, a factor of 50 short. The paper's conclusion on this point is unusually blunt for the genre. No X-ray flare will ever be able to evaporate a disk such as this one. And across 6 separate X-ray observations of the star, not a single flare was seen. The Chandra light curve is flat. A variant involving coronal mass ejections rather than flares was proposed, and rejected on the opposite grounds. The events required would recur roughly every 9 days, which means the disk should never have been able to exist for 25 years in the first place. If that mechanism were operating, there would have been nothing to lose. Restructuring of the inner disk so that it shadowed an outer disk was rejected because the energy intercepted by the inner region would have to reappear at shorter wavelengths, and it does not. A binary companion carrying its own cold disk, heated at closest approach, was rejected on the geometry and on the interferometric limits, which constrain any companion to below 0.2 solar masses between 0.1 and 4 astronomical units, and tighter further out. 2 explanations survive, and neither of them is comfortable. The first is a collisional avalanche. It works like this. A single collision produces a population of very small grains. Small grains have a large surface area relative to their mass, so the star's radiation pressure blows them outward at speed. Those accelerated grains strike larger grains and shatter them, producing more small grains, which are also accelerated. The process cascades through the disk, converting large material into small material and then sweeping the small material out of the system entirely. The attractive feature is the trigger. A collision between objects only 100 to 1,000 kilometers across is enough to start it. That is small enough to sit comfortably under every observational limit anyone has. Melis described the mechanism as collisions that instigate a runaway process where small grains chip into oblivion both themselves and also larger grains. The verdict in the 2017 paper is that it survives, while being, in their phrase, dynamically very challenging to realize. The second is runaway accretion driven by gas drag. In the same impact that produced the dust, gas is released. Gas exerts drag on dust grains. Dust grains lose orbital energy, and the whole population spirals inward and falls onto the star. Melis's phrase for the fate of the material was that the gas drags the grains to their doom. This one also survives. And it carries a corollary that is worth sitting with, because it changes what the 25 years of observation actually were. If the gas drag explanation is right, then the excess seen from 1983 to 2008 was never a stable disk at all. It was the debris of the very collision that supplied the gas. Which would mean the quarter-century of steady infrared glow was already the aftermath of something, and we caught only its final chapter, and the beginning of the event happened before anyone had an infrared telescope in orbit to see it. What remains unknown is which of the two is right, and whether the event was genuinely rare or merely rarely caught. Günther put a number on the second question. Comparing the Spitzer and WISE catalogues across a few thousand young stars, he estimated the probability of catching an event like this at about 1 in 100,000. 2 large monitoring programs, covering roughly 11,000 young objects at 3.6 and 4.5 microns, found at most 2 that vanished completely. Only 3 objects with strong mid-infrared variability of this kind are known at all, and this one is by a distance the most extreme. There is a general version of this problem that makes the specific case less lonely and slightly more unsettling. The mechanism generally proposed for these extreme debris disks is the destruction of planetesimals larger than 100 kilometers in a belt that has been stirred up by a planet or a brown dwarf. The difficulty is that the implied destruction rate is so high that it cannot be sustained. The models suggest such activity cannot persist beyond about 1,000 to 10,000 years before the belt runs out of material to destroy. Which means every extreme debris disk we look at is a short-lived phase, and we are always catching them inside a window that is astronomically brief. The surprise is not that one of them changed. The surprise is that it changed while we happened to be pointing at it, and that it changed 1,000 times faster than even that short-lived phase should allow. There is a hole in the record that is worth naming. Between 2013 and 2015 inclusive, no mid-infrared imaging camera was reliably available anywhere in the southern hemisphere. 3 years with no coverage, on an object that changes on a 2-year timescale. Melis suggested that the dust might return within about 10 years, which would have meant sometime around 2019. No follow-up observation from after that date has been published. Either nobody has looked or nobody has said what they found. That is a disk. It was dust, and enough of it to fill an inner solar system, and it left in under 2 years without a single detectable event. The next entry on this list is an entire nebula, and it started going out while people were watching it. Number 5. The nebula that faded in one lifetime. We are halfway down, and it is worth taking one moment to look at what has already changed before we carry on. We began with an object that was never there, reported for 123 years by people who were doing everything right. Then a comet that came closer to this planet than any other on record and left on a path that mathematics cannot follow. Then a comet that split in half in front of witnesses and now arrives only as dust from passages made before Newton was born. Then a half-mile object at the edge of Saturn's rings that was never photographed even once, and whose existence is known entirely from a scratch it left in the ice. And then a disk of planet-building material, enough to fill an inner solar system, which vanished in under 2 years while the star it orbited did not so much as flicker. Notice what has happened to the explanations as we have gone. At the top of the list, the explanation was complete and slightly humbling. By the entry we just finished, the explanation had been narrowed to 2 candidates, both of which the people who proposed them describe as difficult. From here on, the explanations get thinner and the objects get larger. The next entry is a nebula, and it is the only object on this list that a single person could plausibly have watched appear and then watched go out, using the same telescope, within one working life. It is catalogued as Hen 31357. Its central star is SAO 244567, which also carries the variable star designation V839 Ra. It lies in the southern constellation Ara, the Altar, which sits below Scorpius and is not visible from most of the northern hemisphere. And it is known as the Stingray Nebula, a name given to it by Matt Bobrowski for the shape it showed when Hubble first resolved it, a small bright body with 2 lobes and a pair of wavy trailing edges. Its distance is genuinely unsettled, and this is worth flagging plainly, because a figure of about 18,000 light-years circulates widely and exceeds every published estimate. The values in the literature run from about 830 parsecs to nearly 5,000, which is somewhere between roughly 2,700 and 16,000 light-years. Nobody has pinned it down, and it is a reminder that for many objects, the distance is the hardest number to get. What we do know is the angular size, and from that the physical size follows. Its largest angular radius is about 0.8 arcseconds, which is around 1/10 the size of a typical planetary nebula. Small. But 1/10 of a typical planetary nebula is still roughly 130 times the width of our entire solar system, out past the orbit of Neptune. The word small is doing a lot of work. Now the timeline, which is the whole story. In 1967, Carl Gordon Hennize catalogued this object as an A or B type star with hydrogen emission lines. Hennize is a good person to have in this account, an American astronomer who later became a NASA astronaut, flew on the Space Shuttle Challenger in 1985 at the age of 58, and died in 1993 on the north face of Everest. In 1967, this was, to him, an unremarkable entry in a survey of emission-line stars. In 1971, an optical spectrum showed a B1 supergiant central star at an effective temperature of about 21,000 Kelvin, with only weak emission around it. Still unremarkable. This is a star between lives, having finished as a red giant and not yet become a white dwarf, and there was no nebula worth the name. In 1990, bright nebular emission lines and radio emission were discovered around it unexpectedly. The paper that followed, by Parthasarathi, Garcia Lario, Potash and colleagues, carries a title that says, "Everything You Need, SAO 244567, a post-AGB star which has turned into a planetary nebula within the last 40 years. Weak emission in 1971. A fully lit planetary nebula in 1990. The transition happened inside 2 decades. For scale on how unusual that is, a star of this kind normally takes something like a century to become a visible planetary nebula, and the nebula then evolves over thousands to tens of thousands of years. This one did the entire opening act in under 20 years. That is roughly 3 orders of magnitude faster than typical. In 1992 and 1996, narrowband Hubble images finally resolved the shape, and Bobrowski's 1994 paper named it the youngest planetary nebula known, taking that title from an object in the Large Magellanic Cloud. And then it started to go out. Follow the central star's surface temperature, because it is the driver of everything else. About 21,000 Kelvin in 1971 and again in 1980. 38,000 Kelvin in 1988. A peak of 60,000 Kelvin, plus or minus 5,000, in 2002. 50,000, plus or minus 2,500, in 2015. And about 40,000 by 2021. NASA's summary of the first half of that curve is that the star heated up by a factor of 3 in about a decade. The measured heating rate between 1988 and 2002 was 1,570 Kelvin per year. The cooling rate afterwards was 770 Kelvin per year. Its surface gravity tells the same story from the other direction. Expressed as a logarithm, it rose from 4.8 in 1988 to 6.0 in 2002, which means the star was contracting hard, squeezing down and heating up as it did. Then it fell back to 5.5 by 2015, which means the star swelled again. And its wind confirms it. The terminal velocity of the wind streaming off the star rose from 1,800 kilometers per second in 1988 to 2,800 in 2006, and then collapsed to 500 by 2015. Wind speed scales with escape velocity, and escape velocity scales with the square root of surface gravity, so a 5-fold drop in wind speed is direct physical evidence that the star got bigger and looser. 3 independent quantities, measured by different methods, telling the same story. A star that contracted violently, got very hot, and then expanded again, all inside about 30 years. There is also an older trend that nobody has explained. Bradley Schaefer and Ashley Edwards assembled 1,041 brightness measurements of this star, spanning 1889 to 2015, Harvard photographic plates from the 19th century, visual estimates, the ASARS and APAS survey data, and their own modern photometry with the DCAM camera on the 4-meter Blanco telescope at Cerro Tololo in Chile. What they found is that the star's blue magnitude declined slowly and steadily from 10.30 in 1889 to 10.76 in 1980. Then, from about 1980, it fell at 0.20 magnitudes a year, reaching 14.64 by 1996. Read that again. The star had been quietly dimming for 91 years before the dramatic part started. There is no accepted explanation for the 91 years. The definitive measurement of the nebula's collapse came from Bruce Ballack at the University of Washington in Seattle, Martín Guerrero at the Institute of Astrophysics of Andalusia in Granada, and Gerardo Ramos Larios at the University of Guadalajara. They compared archival Hubble images from 1996, 2000 and 2016, and they verified their relative intensities to within 10% using non-variable field stars in the same frames, which is how you prove the change is in the object and not in the telescope. Between 1996 and 2016, the peak count rate in hydrogen alpha fell by 50%. In doubly ionized oxygen, it fell by 33%. And measured as a total flux against the whole record, the doubly ionized oxygen line has fallen by a factor of 900 since 1990. That is the number the press rounded to nearly 1,000. The hydrogen beta flux fell by a much smaller factor of 29, because the two ions occupy regions of quite different density inside the nebula. Some lines went the other way, and the reason is beautiful. Singly ionized nitrogen and singly ionized sulfur actually increased between 1996 and 2016. That is because as the doubly ionized versions of those elements recaptured electrons, they fed the singly ionized populations faster than the singly ionized versions could in turn recombine. The nebula is not simply dimming. It is stepping backwards down the ionization ladder, and you can watch each rung light up as the rung above it empties out. Structurally, the change is drastic. The lobes at the 5 o'clock and 11 o'clock positions vanished completely. The lobes at 2 and 8 o'clock faded slowly, and their tips actually brightened by about 50%. The European Space Agency's summary was that the bright blue shells of gas near the center have all but disappeared, and the wavy edges that earned this nebula its aquatic-themed name are virtually gone. Ballick's own comment: in most studies, the nebula usually gets bigger. Here, it's fundamentally changing its shape and getting fainter on an unprecedented timescale. Guerreros, because of Hubble's optical stability, we are very, very confident that this nebula is changing in brightness. Here is what is physically happening, and it is worth taking slowly. Light crosses this nebula in about a week. That is its light crossing time, and it means the gas has no memory and no lag. The ionization state of the whole structure responds essentially instantly to whatever the central star is doing. A planetary nebula does not glow because it is hot. It glows because ultraviolet light from the central star strips electrons off its atoms, and when those electrons find their way back down, they emit at very specific wavelengths. The nebula is a fluorescent screen, and the star is the lamp. When the star stopped producing enough ultraviolet, the screen began to go dark. Not because anything moved, and not because anything cooled in the ordinary sense, but because the electrons started staying put. The gas is recombining. And the rate at which the light fades is set by nothing more than how long it takes an ion to find an electron at that density, which for the doubly ionized oxygen works out to a recombination timescale of 3.8 years, at a density of about 40,000 particles per cubic centimeter. Extinction has been explicitly ruled out, and the way it was ruled out is elegant. The reddening toward this object is very small to begin with. But more decisively, the radio emission from the nebula changed in step with the changes in the hydrogen lines. Foreground dust cannot dim radio waves. If something was simply drawing a curtain, the radio would be unaffected. It is not. The nebula is not being hidden. It is going out. There is a control built into this observation that makes it very hard to argue with. A companion star lies only 3 to 4/10 of an arcsecond away from the central star, close enough that it sits inside the same Hubble frames in every epoch. That companion has stayed constant in brightness throughout, at 17th magnitude, for the entire period. So the fading is not the telescope, not the calibration, not the atmosphere, and not the archive. One star in the frame held steady while the thing beside it collapsed. There is one methodological trap in the long light curve that deserves saying out loud, because it is the kind of thing that can quietly corrupt a result. The measurements from before 1980 are measuring the star's own continuous light. The measurements from after 1989 are essentially measuring the nebula's oxygen emission line, because by then, the nebula dominates the band. The two halves of that 126-year light curve are not measuring the same thing, and any interpretation has to account for the switch. Balik's summary of the cause, SAO 244567, seems to have undergone a rapid shrinking with a rapid decrease in its ionizing luminosity in the early 1980s. Or, in a phrase from an earlier assessment published in 1995, the nuclear fuel is almost extinct. There is a competing explanation, and it is not really competing so much as offering a different cause for the same collapse. Nicole Reindl and colleagues, working across Leicester, Tübingen, La Plata and Potsdam, published a letter under the title "Breaking News from the HST. The central star of the Stingray Nebula is now returning to the AGB." Their reading is a late thermal pulse. In a star at this stage, helium can ignite in a shell in a sudden flash, and the energy from that flash forces an already very compact object to swell back out to giant dimensions. This is called the born-again scenario, and it happens on timescales of decades, which is exactly why such stars can be watched changing in real time. Hubble ultraviolet spectra taken on the 9th of August 2015 support it. The star has cooled since 2002, and its envelope is expanding. Several alternatives have been examined and set aside. A post-extreme horizontal branch star cannot produce a nebula this young. A stellar merger would leave an odd surface composition and broadened spectral lines from rapid rotation, and the lines here are narrow. A star emerging from a common envelope with a close companion would contract toward white dwarf status rather than re-expand. And the composition argues for a modest star, largely solar abundances, thin disk population with solar helium and nitrogen that rule out a second dredge-up, and a subsolar carbon abundance implying an initial mass below about 1.5 solar masses. This was not an exotic object. It was an ordinary star doing something nobody predicted. The closest analog anyone has found is an object called HuB1, whose central star dimmed by about 10 magnitudes, a factor of 10,000, in 50 years, and whose nebula is also recombining. But the Stingray remains unique in one specific respect. It is the only planetary nebula of its type whose central star was monitored for a century before it faded. We have the before. Objects of that kind are rare. There are essentially three others: V605 Aquilae, V4334 Sagittarii, which is usually called Saccharie's object, and FG Sagittae. And this one is the only star of the group ever observed during both the heating phase and the cooling phase. We have the whole arc. What remains unknown is a genuine contradiction, and it has not gone away. The star's mass will not resolve. Its position in the temperature and gravity plane, compared against the standard evolutionary tracks, requires a central star below 0.53 solar masses. Its rapid heating rate requires at least 0.7, and one analysis puts it at 0.79. Those two constraints are mutually incompatible, and there is no third measurement that breaks the tie. A model star at 0.50 solar masses peaks near 28,000 Kelvin, which is barely enough to ionize the nebula at all, and evolves too slowly. A model at 0.71 reaches 100,000 Kelvin and evolves far too fast. Nothing in between fits everything at once. Reindl's conclusion is that none of the current models can fully reproduce the evolution of all the surface parameters simultaneously. Her summary of the object is the best single sentence written about it. SAO 244567 keeps on challenging stellar evolution theory. Bialik's version is shorter. The recent evolution of this star, he wrote, is a conundrum. The most recent follow-up used the Southern African Large Telescope's high-resolution spectrograph in May and June of 2021, and it confirms that the recombination is continuing. High ionization lines decreasing, low ionization lines increasing. The Nebula excitation class has fallen from about 9 in 1990 to about 4 in 2021. The star sits at 40,000 Kelvin and is still cooling. One assessment puts it flatly: the Stingray Nebula seems destined to vanish in the next few years. And yet the prediction from the 2020 work leaves a door open, and it is the most remarkable thing in this entry. The ionization, they wrote, will slowly recover if the star finds its way back onto a standard evolutionary track, perhaps in a few decades. Which would make this the only planetary nebula in the sky that a person could watch go out and then live long enough to watch come back. A nebula is a star's outer layers, thrown off and lit from within. The next entry on this list is the star itself, and the star weighed as much as 100 suns. Number 4, the star of 100 suns. About 75 million light-years away, in the constellation Aquarius, there is a small galaxy called PHL 293b. It also goes by the name of the Kinman Dwarf, after Thomas Kinman, who catalogued it in 1965. It is a blue, compact dwarf galaxy, which is a small, chemically primitive system in the middle of forming stars, and it is entirely unremarkable except for one thing. Between 2001 and 2011, 4 separate spectra of that galaxy showed the unmistakable signature of a single star. Broad hydrogen emission lines with P Cygni profiles, iron features, weak helium, all of it consistent with one object radiating between 2.5 and 3.5 million times the luminosity of the Sun. In 2019, astronomers pointed the largest optical telescopes on Earth at that galaxy in order to study the star in detail. The signature was not there. The inferred initial mass of that star was somewhere between 85 and 120 times the mass of the Sun. If it collapsed, it would have made a black hole of 40 to 90 solar masses. Andrew Allen of Trinity College Dublin, who led the work with Jose Gros, framed the problem in one sentence. "It would be highly unusual," he said, "for such a massive star to disappear without producing a bright supernova explosion." Before we go into what happened, it is worth understanding why anyone was watching this particular galaxy in the first place, because the reason is more interesting than the coincidence it might sound like. The Kinman Dwarf has a stellar mass of about 20 million times the Sun. The Milky Way has something on the order of 60 billion solar masses in stars, so this galaxy is roughly 1/3000th of ours. 3/4 of its ordinary matter is still neutral hydrogen gas that has never been made into anything. And its oxygen abundance is about 1/10 of the Sun's, which is half that of the Small Magellanic Cloud, itself famously metal-poor. That chemical primitiveness is the point. Massive stars behave differently when they have very little in the way of heavy elements. The winds that pour off a massive star are driven by radiation pushing on metal ions in the outer layers, so a star with fewer metals has a weaker wind and holds onto much more of its own mass through its life. Which means that metal-poor massive stars are the closest thing available to the very first generation of stars in the universe, the ones that formed out of hydrogen and helium alone, and that nobody will ever observe directly. Studying a 100 solar mass star in a galaxy with 1/10 of solar metallicity is studying a fossil behavior. PHL 293b and a galaxy called DDO68 are the only 2 low metallicity galaxies where luminous blue variables have ever been detected at all. And the record on this galaxy goes back further than the spectra. Kinman catalogued it in 1965 from Palomar Sky Survey plates and from 1949 plates taken with the Lick Carnegie astrograph, giving what he described as a very rough estimate of the blue magnitude of 17.7. Neither Kinman in 1965 nor a follow-up study in 1980 mentions any broad emission at all. Whatever this star was doing in 2001, it was not doing it in the 1960s and 70s. Something started. The signature was first identified by Yuri Izotov and Trinh Thuan in 2009 using a Sloan Digital Sky Survey spectrum taken on the 22nd of August 2001 and a Very Large Telescope spectrum taken with the UVS instrument on the 8th of November 2002. Spectra from 2001, 2002, 2009 and 2011 were remarkably similar to one another, differing mainly in the strength of the narrow components. Allen and his colleagues read that decade of stability as confirmation that they were looking at a single star in a sustained eruptive state rather than at some transient that had already come and gone. The parameters they modeled are extreme even by the standards of massive stars. A luminosity between 2.5 and 3.5 million times the Sun's. A mass loss rate between 5 and 20 thousandths of a solar mass per year, stated explicitly as a lower limit, which means this star was throwing off at least the mass of Jupiter every day or two, continuously, for years. And a wind terminal velocity of 1,000 kilometers per second. That last number is worth a comparison, because it is the one that classifies the object. The red supergiant VY Canis Majoris, one of the largest stars known, drives its wind at about 40 kilometers per second. A star in a classic S Doradus outburst, the standard behavior of a luminous blue variable, runs at 50 to 300. 1,000 kilometers per second is eruption class. That is a star tearing at itself. And the signature itself is diagnostic. Broad hydrogen emission with P Cygni profiles, which is the characteristic shape you get when material is expanding toward you and away from you at once, producing emission on one side of the line and absorption blue shifted on the other. Plus iron and weak helium. As Allen's team wrote, only luminous blue variables show these types of signatures. It is not an ambiguous fingerprint. There is one more constraint worth putting on the table before we get to the observation, because it bounds how much room there is for the star to be hiding. If a star did survive, concealed inside the noise of the 2019 spectra, the limits require it to have a luminosity below 380,000 times the Sun's, and a mass loss rate below about 3,000ths of a solar mass per year. Compare that against what it was doing, 2.5 to 3.5 million solar luminosities. Even the survival scenario demands the star dropped its output by between 85 and 92%. There is no version of this story where nothing much happened. And the initial mass estimate comes with its own caveat, which the team stated openly. The 85 to 120 solar masses assumes the star lived alone. It could have been significantly lower, they wrote, if the star was a mass gainer in a binary system, pulling material off a companion and appearing more massive than it was born. Massive stars are overwhelmingly found in pairs, so that is not a remote possibility. So in 2019, they went to look at it properly. Picture the night. Paranal, in the Atacama Desert of northern Chile, at an altitude of 2.5 kilometers in some of the driest air on the planet. 4 telescopes stand on the ridge, each with a primary mirror 8.2 meters across. Ordinarily, they work separately. But they can be operated in a combined mode, where light from all 4 is fed down through tunnels beneath the mountain and brought together into a single instrument. On the 28th of August, 2019, That is what was done, and the instrument at the end of the light path was Espresso, a spectrograph with a resolving power of 72,000. That is the largest optical collecting area ever assembled to feed one spectrograph. 4 8-meter mirrors, 4 separate mountaintop structures, a network of underground light paths, and the entire apparatus pointed at a faint smudge of a galaxy 75 million light-years away in order to find the fingerprint of one star. The spectrum comes up, and the lines that 4 previous spectra had recorded are not in it. No broad hydrogen with P Cygni profiles. No iron. No helium. There is a particular quality to that moment that is worth naming. A null result on the best instrument ever built for the job is not a failure of the observation. It is the observation. There is nothing to recheck, nothing to try harder at, no fainter setting to reach for. You have used everything there is. They followed up with the X-Shooter instrument later the same year. Same answer. Independent confirmation came quickly from Colin Burke at the University of Illinois, who obtained a spectrum with the GMOS instrument on Gemini North on the 20th of December 2019, under director's discretionary time. His numbers put figures on it. The broad hydrogen alpha luminosity had fallen from 1.3 times 10 to the 39th ergs per second in 2001 to 2.6 times 10 to the 38th in 2019. That is an 80% decrease. The ratio of broad to narrow emission fell from 0.41 to 0.10, and an ultra-broad red wing in the line, which a competing model had depended on, was, in his words, no longer present in the Gemini data. Allen's team dated the loss to somewhere between 2011 and 2016, with the signature absent from 2016 onward. Which means the eruption had run for at least 8.5 years, steadily, and then stopped. There are 3 explanations on the table, and this is where the entry gets interesting, because none of them has won. The first is the modest one, and Allen's team offered it themselves rather than waiting for someone else to. The eruption ended. A luminous blue variable in outburst can settle back down. The luminosity drops somewhat, the surface gets hotter, the spectrum changes shape, and some of the enormous quantity of material the star has been shedding condenses into dust that obscures what is left. This does not require the star to be gone. It requires the star to have stopped shouting. And crucially, this scenario does not require a sudden end to the eruption, which makes it comfortable with the 6-year window in which the change happened. The second is the one that made headlines around the world. The star collapsed directly into a black hole without producing a bright supernova. A failed supernova of the kind we will meet again in the very next entry, possibly with a weak transient that nobody caught. If that is what happened, it is remarkable for a reason beyond the disappearance itself, and this is the part most coverage missed. As Allen's team pointed out, a spectroscopic observation of a star immediately preceding its collapse to a black hole without a bright supernova would be unprecedented. Consider how rare that class of data is in general. Pre-explosion and post-explosion spectra exist for exactly one supernova in history, SN 1987A, and for 2 contested candidates. Here, there are several spectra of the star itself, taken across a decade before it went. If the collapse interpretation is right, then in the archives of the Sloan Survey and the Very Large Telescope, there are portraits of a star that no longer exists, taken without anyone knowing what they were photographing. The third explanation came from Burke, and it reframes everything. On his reading, this was never a star behaving as a star. It was a long-lived stellar transient, most likely a Type 2N supernova that had already happened, whose glow was sustained for years by the blast wave plowing into dense material the star had shed beforehand. His timing puts the event between September 1995 and September 1998, and that window is not arbitrary. It sits inside a genuine hole in the record. There is a gap in the photometry, he noted, between September 1995 and the beginning of the Sloan data in September 1998. 3 years with no coverage, right where the event would have to be. His energy argument is economical. Sustaining broad emission at that luminosity for 15 years requires about 5 times 10 to the 47th ergs, which is comfortably below the canonical supernova energy budget of 10 to the 51st. There is plenty in the tank. And he raised a pointed objection to the luminous blue variable reading, an 800 km per second terminal velocity, he noted, would be the largest ever reported for such a star. Eta Carinae, the most famous luminous blue variable in our own galaxy, runs at about 500. There is a detail about that exchange worth keeping, because it tells you what kind of field this is. The referee of Burke's paper was Roberto Terlevich, who had himself published a third interpretation, that the whole thing was an expanding shell driven by the wind of a young star cluster rather than a single star at all. A man reviewed the paper that argued against his own model and recommended it. And then, in 2022, the story turned over. Natalia Guseva, with Trin Thuan and Yuri Izotov, the same Izotov and Thuan who had identified the signature in the first place 13 years earlier, published a decade of monitoring. 6 spectra, the Sloan observation of 2001, 4 taken with the 3.5-meter telescope at Apache Point in 2010, 2014, 2015, and 2017, and 1 taken with the Large Binocular Telescope in November 2020. Their headline finding is the opposite of a disappearance. Unusually persistent P Cygni features, they wrote, are clearly visible until the end of 2020, despite a decrease of the broad to narrow flux ratio. The broad component was still detectable at around 2 times 10 to the 38th ergs per second at the end of 2020, which is after every epoch Allen's team had used. There is also a cross-team inconsistency that nobody has reconciled. A separate group detected P Cygni profiles in July 2017 using the 10.4-meter Gran Telescopio Canarias, the largest single optical telescope in the world. Burke found none in December 2019. 2 large telescopes, 2 years apart, opposite answers. Guseva's own data cut both ways, to be fair to everyone. The ion emission lines characteristic of erupting luminous blue variables were not detected in any of the new observations, including 2020. And her team offers a useful criterion, which is that a genuine luminous blue variable should show its features strengthen and then disappear. In the neighboring dwarf galaxy DDO 68, that is exactly what was seen. Hydrogen alpha rose by more than a factor of 1,000 between 2008 and 2010. The P Cygni profiles were gone by early 2012, and the broad components by 2018. A clean 5-year outburst with a clean end. PHL 293b did not do that. Stand back from the whole exchange for a moment, because there is something worth noticing in it that has nothing to do with astrophysics. Izotov and Thuan find the star's signature in 2009. Allen and Groh report in 2020 that it is gone and may have collapsed without exploding. Then in 2022, Izotov and Thuan, with Guseva, publish a decade of monitoring and report that the features were still visible at the end of 2020. Nobody in that sequence is careless. Nobody is wrong about their own data. Every measurement any of them made is, as far as anyone can tell, correct. And the fate of a star 100 times the mass of the Sun currently depends on which spectrum you happen to be holding, and every person involved knows it, and they all keep observing. That is what an unresolved question actually looks like from the inside. Not a mystery in the dramatic sense. 4 teams, several very large telescopes, 20 years of data, complete professional respect, and no agreement. And there is a comparison worth making before we move on. 2 entries ago, we talked about a disk of dust vanishing around a young star, and Carl Mellis called it enough dust to fill an inner solar system. Set that against this. This star was shedding at least 5/1000ths of a solar mass every year. Galaxies will continue to drift. The stars overhead may appear eternal, but the great web of galaxies is always in motion. The quantity that was astonishing at number 6 is a rounding error here. It is also worth noting what this galaxy has never done. It has never been detected in X-rays, a 7.7 kilosecond exposure with Chandra in 2009 sets the upper limit. It has never been detected in radio, across the NVSS survey of 1993, the first survey of 2002, or the more recent VLA Sky survey. If a supernova had gone off there and were still interacting with dense material, X-rays and radio would be the natural places to look, and both are silent. Burke himself noted that the X-ray non-detection suggests a non-terminal outburst rather than a true explosion, which cuts against his own preferred reading. The line widths tell a story too, if you follow them. The broad hydrogen alpha component had a full width of about 1,500 kilometers per second in 2001, about 1,000 in 2009, and then after 2010, the broad components narrowed dramatically to somewhere between 160 and 180. That is not a light going out. That is something slowing down. Burke offered a clean, falsifiable prediction, which is the most useful thing anyone in this argument has done. If the supernova was terminal, he said, there will be little or no continued variability. If the progenitor is still present, there will be continued small amplitude variability. The measured variability from Sloan photometry between 1998 and 2005 and dark energy survey imaging between 2013 and 2018 is 0.12 magnitudes in the green band over 20 years. That is a 10% luminosity swing, and it is statistically significant at 11 sigma. Something is still varying. The decisive test on this object has not been done. Hot dust above 1500 Kelvin is ruled out because the near-infrared continuum did not change between 2009 and 2019. But a slowly expanding shell of cooler dust would only show up in the mid-infrared, and no such observation has been published. One measurement, with the right instrument, would settle whether there is a star hiding behind its own smoke. Nobody has made it. So here is the honest status. The signature that 4 spectra recorded across a decade is not present in 2019 data from the largest telescopes on Earth. Whether the star died, dimmed, hid behind its own dust, or was never quite what everyone thought, is not settled. One team says the disappearance was real and possibly unprecedented in the history of the science. Another says it never fully disappeared at all. Both of them are looking at the same galaxy. That star may have collapsed without an explosion. It may still be there. The next entry on this list is the only case where astronomers went looking for exactly that, on purpose, and kept looking for 17 years. Number 3, the supergiant that failed to explode. In the spring of 2009, a red supergiant star of about 25 solar masses, brightened by a factor of roughly 100, reaching more than 1 million times the luminosity of the Sun. It did not become a supernova. It faded. It faded past its original brightness, and then it kept fading, and by 2015 it was at least 5 magnitudes dimmer than the star that had been there before, which is to say 100 times fainter, which is to say that in visible light it was simply not there anymore. The object is catalogued as N6946BH1. The letters at the end are not decorative. It is the leading candidate for a phenomenon that has been predicted since 1980 and has never been confirmed. A massive star that collapses directly into a black hole without an explosion. A star that goes out instead of going off. The galaxy it happened in is worth knowing. NGC 6946 straddles the border between Cepheus and Cygnus, and it is called the Fireworks Galaxy, for a reason that is entirely earned. 10 supernovae have been recorded in it since 1917. The list runs: 1917A, discovered by George Ritchie in July of that year; 1939C, found by Fritz Zwicky; 1948B, 1968D, 1969P, 1980K, 2002, HH, 2004 ET, 2008S, and 2017 EAW, discovered by the amateur astronomer Patrick Wiggins in May of that year. 10 supernovae in a little over a century, from a galaxy that has roughly half as many stars as the Milky Way. That is about 10 times our galaxy's rate. For most of the past several decades, it held the record for the most supernovae observed in a single galaxy. William Herschel discovered it on the 9th of September, 1798, and its disk spans about 87,000 light-years, comparable to our own. Its distance is genuinely uncertain, and it is worth flagging because different papers on this very object use different values. Estimates in use run from about 5.9 to 7.7 megaparsecs, which is roughly 19 to 25 million light-years. The galaxy also sits behind a substantial amount of dust in our own galaxy's plane, which reddens everything and makes every measurement harder than it should be. Now the part that makes this entry different from every other item on this list. Somebody went looking for this. On purpose. Before it happened. In 2008, Christopher Kokenek and Christoph Stanek at Ohio State University, with colleagues, began a survey using the Large Binocular Telescope in Arizona, designed for one purpose: to find failed supernovae. The Large Binocular Telescope carries 2 8.4-meter mirrors on a single mount, giving it the light-collecting area of a single 11.8-meter telescope, and this survey uses it in the least glamorous way imaginable. It takes the same pictures of the same galaxies over and over for years. The design is simple and enormously patient. Monitor 27 galaxies within about 30 million light-years. Catalog every luminous star in all of them. And then wait for one of them to stop being there. The master catalog runs to 6.3 million individual sources. The filtering process tells you how hard this is. Of 13,223 flagged candidates, 82% turned out to be artifacts of the image subtraction process, and 15% were ordinary variable stars doing ordinary variable things. That left 317. Further work reduced that to 151, and the final count of genuine candidates was 5. 5 out of 6.3 million sources in 17 years. But the survey has produced an actual number, which is the thing that matters. From 11 years of data, the measured fraction of massive stars that die this way is 0.16, with a 90% confidence range running from 0.04 to 0.39. Roughly 1 in 6 massive stars may end without an explosion. If that holds, then a substantial fraction of the biggest stars in the universe simply switch off, and nobody has ever seen it clearly enough to be certain. It is worth dwelling for a moment on what that survey design actually asks of the people running it. Almost every observing program in astronomy is structured around detection. You point at something, you hope it is there, and a positive result is a paper. This program is structured around the opposite. Its success condition is that a star that has been sitting in the same pixel for years is no longer in that pixel, and to establish that, you have to eliminate every mundane reason a star might look fainter this year than last: the seeing, the calibration, the subtraction algorithm, ordinary variability, dust drifting across the line of sight. 82% of the candidates were the algorithm being wrong about its own arithmetic. 15% were stars being stars. Somebody had to decide, in 2008, that absence was worth building a career around, and then had to keep pointing the same telescope at the same 27 galaxies for the next 17 years, on the expectation of finding, at best, a handful of things that were not there. Here is what was observed. The star before the event was a red supergiant of about 25 solar masses, radiating around 430,000 times the Sun's output, at a surface temperature near 3,500 Kelvin. Roberta Humphreys has argued it was a yellow hypergiant rather than a red supergiant, which is a live disagreement and worth noting. The temperature fits across 10 different models, span roughly 2,900 to 6,700 Kelvin, which is a fair reminder of how much of this rests on modeling rather than direct measurement. The outburst was caught by the Palomar Transient Factory. First detection on the 17th of March 2009 at red magnitude 19.0. Last detection on the 26th of May 2009 at 19.6. Over that spring, the star's total output rose to at least 1 million times the Sun's. Astronomers describe that as a weak outburst, which is a strange adjective for something 1 million times brighter than the Sun. But on the scale of stellar death, it really is nothing. A supernova reaches roughly 100 million times that. What happened here was, by the standards of what usually happens when a 25 solar mass star runs out of fuel, a flicker. And then the crucial detail, the one the whole interpretation turns on. It did not fade back to where it started. It faded straight past its own previous brightness and kept going, ending up around 100,000 solar luminosities below where it had been before the event began. Hubble imaging with the Wide Field Camera 3 on the 8th of October 2015 and Spitzer imaging on the 21st of January 2016 confirmed the optical source was gone, measured against a Hubble reference image taken on the 8th of July 2007. The closest surviving source in the post-event data sits 0.045 arcseconds from the progenitor's position, and the probability of a comparably bright, unrelated source landing that close by chance is about 0.9%. What is left is a faint infrared remnant of 2,000 to 3,000 solar luminosities. That is less than 1% of the original star. The mid-infrared is at its lowest level since 2004, and the remaining total output is more than 6 times fainter than the progenitor, declining as time to the power of -4/3. That decline rate is not a throwaway detail. It is close to the theoretical curve for material falling back onto a newly formed black hole, which is exactly what the failed supernova picture predicts should happen after the collapse. The light we are seeing now, on this reading, is not the star. It is debris being eaten. Scott Adams, Kochenek and colleagues concluded in 2017 that the late-time behavior is inconsistent with obscuration from an ejected, dusty shell, and that the event is unlikely to be a supernova imposter or a stellar merger. What fits is a failed supernova, the envelope ejected, the core collapsed, material now falling back. The theory behind this was worked out decades before there was any candidate to test it against, and it is worth taking slowly because it is one of the more counterintuitive pieces of stellar physics. Go inside a massive star in its last second. The core has run through hydrogen, helium, carbon, oxygen, silicon, and it has built itself an iron center. Iron does not burn. Fusing it costs energy rather than releasing it. So the support underneath the star's own weight gives way, and the core collapses in a fraction of a second down to nuclear density. In that collapse, an enormous quantity of energy is radiated away as neutrinos. Neutrinos barely interact with matter at all. They pour straight out through the star, as though it were not there. And the amount involved is not small. Between 2/10 and half a solar mass of the star's own mass is converted into neutrinos and gone within seconds. Here is the consequence, worked out by Dmitry Nadezhin in 1980 and developed by Elizabeth Lovegrove and Stan Woosley in 2013. The outer layers of the star were being held down by the gravity of the core. The core has just lost up to half a solar mass of mass energy. So its gravitational grip weakens by exactly that much, instantly, everywhere, at the speed of light. A weak pressure wave runs outward through the star, and because a red supergiant's outer envelope is enormously extended and only loosely bound, that wave is enough to unbind it and push it away. Meanwhile, the core has nothing left holding it up. It falls straight through and becomes a black hole. The predicted observable signature of that sequence is a brief breakout flash of around 10 million solar luminosities lasting 3 to 10 days, followed by a roughly year-long transient at about 3000 Kelvin and 1 million solar luminosities as the ejected envelope cools and its hydrogen recombines, which is very nearly what was seen in 2009. There is a separate reason the field wants this to be real, and it is called the red supergiant problem. When astronomers identify the progenitor stars of ordinary Type 2P supernovae in archival images, the masses cap out around 18 solar masses. But red supergiants exist up to 25 and beyond. Something is happening to the largest ones, and they are not turning up as supernovae. Failed supernovae would account for that neatly. They would also explain the observed gap in mass between the heaviest neutron stars and the lightest black holes, because the black hole formed this way has the mass of the star's helium core rather than of some smaller remnant. And they may be needed to explain the heaviest gravitational wave detections, the 36 and 29 solar mass black holes that merged in the first detection ever made, are difficult to produce by any other route. The argument over this particular star is live right now, and it is the kind of disagreement worth watching rather than resolving prematurely. On the 25th of August, 2023, 14 years after the disappearance, the James Webb Space Telescope observed the field with its NIRCam and MIRI instruments. Emma Bisa and colleagues concluded in 2024 that every previous observation had been a blend of at least 3 separate sources rather than one, that the total luminosity there is 13 to 25% of the progenitor, that the mid-infrared is actually brighter than the progenitor model predicts, and that the spectral shape shows features consistent with the large carbon-based molecules that astronomers call polycyclic aromatic hydrocarbons. Their verdict, carefully phrased: the observations match expectations for a stellar merger, but theoretical ambiguity in the failed supernova hypothesis makes it hard to dismiss. That has been contested in turn. A 2026 analysis by Forés Toribio and Kochenek argues that the source position was misidentified, that the relevant Webb source sits 0.018 arcseconds from the pre-event Hubble star, and that the nearby red objects Bisa's team folded in are unrelated red giants that happen to lie along the same line of sight. They argue the mid-infrared feature is silicate absorption rather than hydrocarbon emission, and they support that with a comparison spectrum from a similar object in Andromeda. and they offer a clean discriminator, which is the most useful contribution to the argument so far. Merger remnants end up 10 to 100 times brighter than their progenitors, because a merger is a violent release of energy that leaves an inflated, luminous object behind. Failed supernova remnants end up around 10 times dimmer because the star is gone, and what remains is a trickle of fallback. This object is dimmer. Their large binocular telescope record now runs to 56 separate observing epochs between May 2008 and September 2025, and across all of them, the post-outburst flux is statistically indistinguishable from zero, with a measured trend of -2.1 plus or minus 24.5 solar luminosities per year, which is a very precise way of saying nothing. There is a further consequence of this mechanism that is worth stating, because it changes what a black hole's mass means. In an ordinary supernova, the explosion blows off most of the star, and what falls back to form the remnant is a fraction of the core. In a failed supernova, essentially the whole helium core goes in, because there is no explosion to interrupt it. So the resulting black hole inherits the mass of the helium core directly, which is a much larger and much more predictable quantity. That naturally produces black holes in a specific mass range, and it naturally produces a gap below that range where nothing forms. Astronomers have measured such a gap between the heaviest neutron stars and the lightest black holes for years, and have struggled to explain it. This mechanism explains it as a straightforward consequence of which stars explode and which do not. There is one other candidate, and it is closer to home. M31 2014 DS1 in the Andromeda Galaxy faded by at least a factor of 100 in visible light between 2016 and 2019. A Webb observation on the 28th of November 2024 found it at about 7% of the progenitor's luminosity. Chandra found 0 X-ray counts from it, which argues against the remnant being powered by accretion. And Chandra found no X-rays from N6946BH1 either. The survey that found all of this also rejects its own candidates, which is worth saying out loud because it is the mark of a healthy program. A new candidate, M1010C1, has been reported, a blue supergiant that vanished with no sign of warm dust to hide behind. Another candidate, N47360C1, was withdrawn after 2021 observations showed it was still there. It is worth registering how strange the theoretical situation is here. The red supergiant problem itself is disputed. Ben Davies and Emma Bisa argued in 2020 that the apparent upper mass limit on supernova progenitors is a statistical artifact of small samples and uncertain mass estimates, and Kokonek defended it the same year. So one of the main motivations for expecting failed supernovae to exist is under active argument, at the same time as the best candidate for one is under active argument, by overlapping groups of people. Modern calculations of which stars can explode and which cannot suggest that somewhere between 10 and 30% of core collapses fail, which brackets the survey's measured 16% comfortably. But the theory has enough freedom in it that it is not currently able to rule anything out on its own. So the honest state of this entry is as follows. The star is gone. The survey that caught it was purpose-built to catch exactly this, by people who had thought carefully about what absence would look like before they started looking. The fading curve matches a decades-old theoretical prediction, and two teams working from the same James Webb dataset have reached opposite conclusions about whether what remains is a black hole quietly consuming the last of its own star, or 3 ordinary stars that were always there and were never properly resolved until now. One star can go out quietly, and it takes 25 solar masses with it. The next entry on this list is the brightest kind of object the universe knows how to make. and some of them switch off in under 2 years. Number 2. The quasars that turn off. A quasar is the brightest sustained object the universe knows how to make. Not the brightest event. Supernovae and gamma-ray bursts are brighter for a few weeks. The brightest thing that stays bright. At the center of a galaxy sits a supermassive black hole, and around it a disk of gas spiraling inward, and as that gas falls it is compressed and sheared and heated until it radiates more light than every star in the surrounding galaxy combined. Some of them outshine their entire host galaxy by a factor of 100. The standard picture says these engines run on very long timescales. An active phase lasts somewhere between 100,000 and 1 billion years. And the inner accretion disk, the part that produces most of the light, cannot restructure itself in less than centuries, because the material in it has to physically move inward, and the rate at which it can do that is set by how efficiently friction can carry angular momentum outward. Some of them turn off in under 2 years. Not dim. Not flicker. Turn off. The broad emission lines that define the object as a quasar disappear from its spectrum entirely. The continuum falls by factors of 10, 50, 100. The galaxy is still there. The black hole is still there. The thing that made it a quasar is not. These are called changing-look active galactic nuclei, and there is a distinction inside the category that matters a great deal. Some of them are changing obscuration, which means a cloud of dust has drifted across the line of sight and the engine is running fine behind it. Others are changing state, which means the accretion itself has changed. It is the second kind that breaks the physics, and separating the two took 2 decades of careful work. It is worth setting out the classification scheme properly, because the whole phenomenon is defined against it. Active galaxies come in 2 headline types. A Type 1 shows both broad emission lines, with widths above about 1,000 kilometers per second, and narrow ones. A Type 2 shows only the narrow lines. For half a century, the standard explanation for that difference has been geometric. The broad line region sits close to the black hole and is surrounded by a thick donut of dust, so whether you see the broad lines depends entirely on whether you happen to be looking down the hole of the donut or at its side. Same object, different angle. That model has been extremely successful. And a single object that changes from one type to the other and back directly contradicts it, because we cannot have moved. Something about 70% of nearby active galaxies are obscured to some degree, and 20 to 30% are so thickly obscured that even hard X-rays struggle to escape, so disentangling a genuine change of state from a change in what is in the way was never going to be quick. It took decades, and the 10 arguments we will come to are the result. One more piece of calibration. Ordinary active galaxy variability rarely exceeds a few tens of % in the optical continuum. These objects change by factors of 10 to 100. They are not the tail of a normal distribution. They are doing something else. The best documented case has a 40-year record behind it. Markarian 590, which also carries the catalog name NGC 863, sits at a redshift of 0.026, about 340 million light-years away. In the 1970s, it was a textbook example of a bright, active galaxy of the type astronomers call a Seyfert one, with strong, broad emission lines and a powerful ultraviolet and X-ray continuum. Through the 1980s and 90s, it got brighter by factors of tens. Then it fell. By 2013, work led by Mitchell Denny using Hubble, Chandra, and the Large Binocular Telescope showed the continuum luminosity a full factor of 100 below its peak, with the broad emission lines all but gone. On the standard classification scheme, it would now be catalogued as a Seyfert 1.9 or even a 2, a different type of object entirely, with only a weak trace of broad hydrogen alpha left in the spectrum. Recent X-ray observations show zero intrinsic absorption along the line of sight. There is nothing in front of it. The engine dimmed. Its black hole mass is unusually well measured because it was one of the objects used to establish the technique. From 102 spectra taken between 1989 and 1996, the reverberation mapping method gives 47.5 million solar masses. That method works by timing how long the gas surrounding the black hole takes to respond to changes in the central light source, which gives you the size of the emitting region, which combined with the gas velocity gives you the mass. It is one of the few direct measurements available. And here is the number that makes this entry work, and it deserves a moment on its own. The entire 70-year event, the rise through the 90s and the collapse afterwards, required the black hole to accrete only 1 to 2 solar masses of material. 1 or 2 ordinary stars' worth of gas. Think about what that means. An object visible from 340 million light-years away, capable of outshining 100 billion stars, running on a total fuel consumption of about the mass of the Sun over a human lifetime. Everything a quasar appears to be is a thin, temporary condition of a very small amount of material that happened to be in the wrong place. It is not a structure. It is a circumstance. And Markarian 590 has since done something nobody predicted. The broad lines came back after about 10 years, though the continuum remains roughly 10 times below its 1990s peak. It did not die. It flickered. The other cases fill out the picture. SDSSJ0159 plus 0033 at redshift 0.31 was the first object formally described as a changing-look quasar. Between 2000 and 2010, it went from a Type 1 quasar to a Type 1.9. The flux fell by a factor of 6, the broad hydrogen alpha line faded and broadened, and the X-rays fell in step with no obscuration signature at all. A re-observation with the 5-meter telescope at Palomar in July 2014 found it unchanged since 2010. It has stayed off. SDSSJ1011 plus 5442 is the sharpest case in the literature. Its continuum at 5,100 angstroms fell by more than a factor of 9.8 in under 9.7 years of rest frame time. Its broad hydrogen alpha line fell by a factor of 55. And the narrow emission lines did not change at all. That last detail is the diagnostic that rules out almost everything else, and it is worth understanding why. The broad lines come from gas very close to the black hole, within light days to light weeks. The narrow lines come from gas much further out, hundreds to thousands of light-years away. If the central engine dims, the nearby gas notices within weeks, and the distant gas will not notice for centuries. That is exactly the pattern observed. The inner region has responded, and the outer region has not been told yet. Photometry from the Catalina survey puts the whole transition inside about 500 rest frame days. Markarian 1018 completed a full cycle, which is rarer still. It changed from Type 1.9 to Type 1 in under 5 years, and then changed back to 1.9 after 30. Its luminosity fell by a factor of 13 to 15 over about 8 years. Its soft X-ray excess collapsed by more than a factor of 60, while its harder X-rays fell only about 7-fold, which means the change was not uniform across the spectrum, but concentrated in the part produced by the inner disk. Its expected cooling front propagation time is about 15 years, and its viscous timescale is 280. It did the job in 8. And then there is 1ES 1927 plus 654, which is the one that was caught in the act. Historically, it was classified as a bare Seyfert 2, an oddity in itself. In late 2017, it flared, and because sky surveys were running continuously by then, it became the first changing state transition ever resolved in time rather than reconstructed from 2 snapshots years apart. The sequence went like this. The blue continuum rose first. The broad hydrogen lines followed 2 to 3 months later, which is exactly backwards from what a passing dust cloud would produce, and exactly right for a central engine brightening and the surrounding gas responding to it. The ultraviolet and optical output rose by more than a factor of 50 in a few months. Then the X-ray corona vanished. The corona is the hot plasma sitting above the accretion disk that produces an active galaxy's hard X-rays, and it is one of the most robust features these objects have. Its power law emission dropped by a factor of 100 or more. That is the first time anyone has watched an accretion corona disappear. About 300 days later, it rebuilt itself. Over that period, the X-ray flux varied by a factor of 10,000 across roughly 100 days, and by a factor of 100 within 8 hours. And the obscuration measured before the event was identical to the obscuration measured after it. Nothing moved in front of anything. Because obscuration is the obvious explanation, it has been tested to exhaustion, and the arguments against it are worth walking through calmly, because together they are what turned this from a curiosity into a problem. A cloud large enough to cover the emitting region would take more than 10 years to cross it. There is no reddening of the light in the dim state, which a dust cloud would necessarily produce. In 1ES 1927, the sequence of events ran backwards from the obscuration prediction. There is no X-ray absorption in the dim states. There is no difference in extinction or column density between bright and dim states. The mid-infrared dims as well, which a foreground screen would not cause, because a screen does not stop the dust further out from being heated. The radio emission varies in a correlated way. The optical polarization stays low. The relationships between color and brightness are normal. And the broad lines get broader when the object is dim, which is precisely what happens if the emitting gas is responding to a fading central source, and precisely the wrong behavior for a curtain being drawn. The mid-infrared argument is the strongest of them. Sheng and colleagues showed in 2017 that 10 changing look objects display large mid-infrared variation that echoes the optical variation with the time lag you expect from dust absorbing and re-emitting the light. That is an echo, not a shadow. The dust further out is watching the central engine change and reporting it back to us a few years late. So the engines really are changing state. Which brings us to the problem. The viscous timescale of an accretion disk, the time material takes to spiral inward through it, works out at roughly 400 years for a 100 million solar mass black hole under standard assumptions, and it can run to tens or hundreds of thousands of years for other configurations. The thermal timescale, the time for the disk to heat or cool, is years to decades. The dynamical timescale, the time for material to orbit, is about 10 days. The light crossing time is under a day. The observed transitions take months to a few years. That is faster than the disk should be able to reorganize itself by 2 to 3 orders of magnitude. Every proposed fix is an attempt to make the inner disk thicker or more magnetic so that things can move faster. Extra opacity from spectral lines, magnetic torques, magnetic pressure support, magnetically driven winds, radiation pressure instabilities, hydrogen ionization instabilities, and disk tearing in disks that are tilted relative to the black hole's spin and precessing. An inner disk inflated so that its height is about a fifth of its radius reproduces the observed timescales. Whether real disks actually do that is not known. There is one reframing that is genuinely elegant. These transitions may be the supermassive analog of the state changes seen in stellar mass X-ray binaries, where a bright, thin accretion disk gives way to a hot, puffy, radiatively inefficient flow once the accretion rate drops below a threshold. The relationship between X-ray and optical output inverts at the same threshold in both cases. If that holds, the same physics runs from 10 solar masses to 10 billion, across 9 orders of magnitude, which would be one of the broader unifications in astrophysics. There is one further scaling relation that makes all of this harder rather than easier. Every time scale in an accretion disk scales linearly with the mass of the black hole. 100 million solar mass black hole should vary about 100 times more slowly than a million solar mass one in every mode. The biggest engines should be the most sluggish objects in the universe, changing on timescales that make them effectively static from a human point of view. And yet some of the fastest transitions on record belong to some of the largest black holes in the sample. The objects that ought to be the least capable of surprising us are among the ones surprising us most. It is also worth noting how much material is required for these changes, because it is not much. Markarian 590's whole 70-year performance ran on 1 to 2 solar masses. The dust that replenishes the inner regions of a typical active galaxy turns over on a timescale of a few years. These are not deep structural transformations of enormous systems. They are small quantities of gas arriving or failing to arrive. What remains unknown is how common this is, and the numbers do not currently agree. Reobserving 102 nearby broad-line active galaxies found that about 38% had changed subclassification, and about 3% had lost the broad hydrogen beta line entirely within 3 to 9 years. But a survey with no photometric preselection found only 19 changing state objects among about 64,000 quasars, which is 0.03%. Those two figures cannot both be describing the same phenomenon until somebody works out how much of each is a selection effect. The best honest description of the total known population is low hundreds. There are older cases in the record that nobody quite knew what to do with at the time. The galaxy NGC 1566 shows 4 separate activity episodes of about 1,300 days each, between 1970 and 1985, and most of its changes during the 1980s took only 4 months. The galaxy IC 3599 flared by more than a factor of 100 in the Rosat X-ray survey, and then repeated the same performance with a similar amplitude 19.5 years later. Those observations sat in the literature as oddities for years before there was a category to put them in. And there is a possibility raised by Denny's team that reframes the whole classification argument. There may be no strict one-way evolution from type 1 to type 2 at all. The broadline region may simply track episodic accretion events inside a single long active phase, appearing when fuel arrives and vanishing when it stops, over and over, for the whole duration of the galaxy's active life. On that reading, the types are not stages and are not viewing angles. They are weather. The largest recent sample found 67% of its objects dimming and 33% brightening, so this is not a one-way process. And the ones that brighten can be stranger than the ones that fade. An object informally called Ansky sat quiet for 2 decades, brightened in December 2019, and from February 2024 began producing quasi-periodic X-ray eruptions every 4.5 days, with a longer 25-day cycle layered on top. Something started up, and it did so with a clock. Here is the thought this entry leaves you with, and it is a calm one rather than an alarming one. If accretion phases last between 100,000 and 1 billion years, and if these transitions take months, then everything a galaxy's central engine appears to be doing is a single frame of a process that flickers on timescales shorter than recorded human history. The quasars in the survey catalogues are not steady lamps that we have measured. They are a strobe, photographed once. We have built a substantial part of our picture of galaxy evolution on the assumption that what a galactic nucleus is doing now is what it has been doing, and a growing number of them are demonstrating, on camera, that this is not a safe assumption. The comprehensive review that pulled all of this together was published in Nature Astronomy in November 2023, and its most useful contribution was insisting on the distinction we started with: changing obscuration on one side, changing state on the other. Everything before that had been a single confusing category with two entirely different physical causes mixed together and a decade of contradictory papers to show for it. Sorting the two apart is what turned a collection of anomalies into a phenomenon with a name and a measured population. An engine that turns off is still an engine that is there. The object at the top of this list is not. Number 1. The black hole that is not at the center of its galaxy. About 2.7 billion light-years from here, in a galaxy cluster catalogued as Abell 2261, sits the cluster's brightest galaxy. It has no name, only a designation, a 2261 BCG, the last 3 letters standing simply for brightest cluster galaxy. It is a supergiant elliptical. It measures about 545,000 light-years across, which is roughly 6 Milky Ways laid end to end. It contains something like 4.4 trillion solar masses of stars. It is one of the largest galaxies anyone has ever measured. And at its center is the largest flat core ever found in any galaxy. That phrase needs unpacking, because it is the whole item. In a normal galaxy, if you plot how the density of stars changes as you move inward from the outskirts toward the middle, the line rises continuously and steeply. More stars, more tightly packed, all the way to the center. In this galaxy, the line rises as expected until you reach a radius of 3.63 kiloparsecs, which is about 12,000 light-years. And then it stops rising. It goes flat. The measured inner slope of the light profile is 0.02, which is not nearly flat. It is flat. For 24,000 light-years across, through the region that should be the densest place in that entire galaxy, the density of stars simply does not increase. Something emptied it. Every scaling relation astronomy has says that a core of that kind is carved out by a supermassive black hole, and that a core that large requires a black hole of extraordinary size. The published estimates for what should be sitting in the middle of that galaxy span from about 5.4 billion to 65 billion solar masses. The two most widely used relations give 25 billion and 39 billion. An independent estimate from the relationship between radio and X-ray emission gives 20 billion. The Chandra X-ray Observatory has looked for it twice. It found nothing. Not at the core. Not at any of the off-center clumps of stars near the core. No point source. No accretion signature. Nothing. That is the object at the top of this list. It is the largest thing anyone has ever reported missing. To follow what is at stake here, you need one piece of physics, and it is one of the more elegant ideas in galactic astronomy. When two galaxies merge, Their central black holes both sink toward the center of the new combined system and eventually form a binary pair, orbiting each other. That pair then does something very specific to its surroundings. Any star that wanders close to the binary gets a gravitational kick from the two moving masses and is flung outward at high speed, and the binary, having given away energy, tightens a little. Then it happens again. And again. Over an enormous number of such encounters, the center of the galaxy is emptied of stars, one star at a time, thrown outward like water off a propeller. The technical term is core scouring. The idea goes back to Martin Rees, Roger Blandford and Mitchell Bagelman in 1980. And it comes with a testable prediction. The mass of stars missing from the core should be roughly half the number of mergers multiplied by the black hole's mass. So you can measure the black hole by measuring the hole. The measurement is a subtraction. You fit the galaxy's brightness profile from the outside in, extrapolate what the center should look like if nothing had scoured it, and weigh the difference between that and what is actually there. For this galaxy, the missing starlight comes to 1.75 times 10 to the 11th solar masses. 175 billion suns worth of stars that are not where they should be. To trim, that is 3.9% of the entire galaxy's stellar mass, against a typical value of under 1% for galaxies of this kind. Expressed against the black hole itself, the missing starlight amounts to about 7 black hole masses. The core is also too large by its own internal standards. For a galaxy of this luminosity, the predicted core radius is 1.2 kiloparsecs. The measured one is 3 times that. Most galaxies with cores of this type have them a few hundred parsecs across. Other measured examples barely exceed 1 kiloparsec. And when Gabriel Bonfini and Alistair Graham reanalyzed the galaxy in 2016, the exercise did what reanalyses almost never do. It made the claim bigger. Their fit gave a larger core than the original, and they wrote that this galaxy can now be reported to have the biggest core of any galaxy of its type. The field is appropriately careful about claims like this, and there is a cautionary tale it keeps in mind. Another galaxy, Home 15A, was reported to have a core of 4.6 kiloparsecs, larger than this one, until reanalysis showed it had no mass deficit at all. The apparent core was an artifact of the fitting. A 2261b CG survived exactly that scrutiny and came out larger. So the hole is real. The question is, what made it? Kehan Gultekin at the University of Michigan, working with Sarah Burke-Spolar, Todd Lauer, Joseph Lazio, John Mustakas, Patrick Ogle, and Mark Postman, went looking. An initial Chandra observation in 2018 found nothing. A deeper follow-up, published in 2021, found nothing again, neither at the galaxy's center nor at any of the star clumps offset from it. Their conclusion, stated with appropriate care, is that the black hole is either accreting at a very low level or has a mass rather below 10 billion solar masses. Their own dynamical estimate comes out at only 6 to 11 billion, which is well under what the core demands. That is the first of 3 uncomfortable answers, and it is the mildest. It says the black hole is there, and quiet, and smaller than the hole it left. Which is a problem in itself, because the whole logic of core scouring is that the hole records the mass. If the object is a fifth or a tenth of what its own excavation implies, then the relationship between a galaxy and the black hole at its center, which is one of the more reliable relationships in extragalactic astronomy, does not hold at the top of the mass range. The second answer is arithmetic, and it does not work either. If you take the mass deficit at face value and run it through the standard scouring relation, Producing a hole that size requires about 14 consecutive major dry mergers, 14 galaxy collisions in sequence, each one involving comparable galaxies, each one with no gas available to form new stars and refill the center. Bonfini and Graham describe that as more than expected from any evolutionary scenario of galaxies. The center of this galaxy is emptier than 14 collisions worth of emptying should manage. And there is a structural clue that points somewhere else. The core is off-center. The innermost contours of light are displaced relative to the galaxy as a whole. The two published measurements of that offset disagree substantially, one giving about an arcsecond and the other giving a fraction of that, a few hundred parsecs, and they should not be blended together. But in either version, the very center of the largest galaxy in the cluster is not where the galaxy's center of mass is. Bonfini and Graham's conclusion contains the sentence this entire countdown has been walking toward. Both our results and those of Postman and colleagues, they wrote, rule out the simple binary black hole scenario, unless the binary has already coalesced and the core has been formed or enlarged by the ejection of the black hole. Which brings us to the third answer. When two black holes finally merge, they emit an enormous burst of gravitational waves in the last fraction of a second. Those waves do not radiate symmetrically. Depending on the masses and, crucially, on how the two black holes' spins are oriented, the emission is lopsided, and lopsided radiation carries momentum. The merged black hole recoils. It gets kicked. Typical kicks are around 100 kilometers per second, which a galaxy easily contains. Certain favorable spin configurations produce what the literature calls superkicks, around 1,000. And for extreme configurations with the spins anti-aligned in the orbital plane, numerical calculations by Manuela Campanelli and colleagues, and by Carlos Lausto and Josef Zlokowa, give kicks of up to about 5,000 kilometers per second. The central escape velocity of a massive elliptical galaxy is about 2,000 kilometers per second. A superkick can throw a supermassive black hole out of its own galaxy. If that is what happened at Abell 2261, then somewhere in the outskirts of that galaxy, or beyond it, there is a black hole of tens of billions of solar masses, moving, no longer at the center of anything. Mark Postman proposed that one of the star knots near the core, a clump of about 7 billion solar masses, might be the stellar cloak that was dragged along with it, the innermost stars, bound tightly enough to travel with the black hole as it left. Bonfini and Graham propose a different knot of 45 billion solar masses as an infalling galactic core that stalled on the way in rather than a departing one. There is a clean test, and it has not been done. A cluster of stars gravitationally bound to a black hole of that mass would have an internal velocity dispersion above 600 kilometers per second. Ordinary compact stellar systems of that size run around 1/100th of that. Measure the velocity dispersion of the right knot, and the question is settled in an afternoon. Nobody has managed it, because the galaxy is 2.7 billion light-years away, and the knots are a few hundred parsecs across. Let me put you there for a moment, because the geometry is worth feeling. You are approaching this galaxy from outside, and it is enormous, 6 Milky Ways wide, a smooth, featureless ellipsoid of old red stars, with no spiral arms, and no dust lanes, and no structure of any kind. You move inward. The stars get denser, steadily, as they should. The sky around you gets brighter. Individual stars are still separated by light years, but there are more and more of them, and the light of the collective grows. 12,000 light years from the center, that stops. You keep traveling inward, and nothing gets denser. The sky does not brighten further. You cross 12,000 light-years of the densest place in a galaxy of 4 trillion suns, and the star count stays flat the entire way, as though someone had drawn a circle and cleared it. The stars that should be here were thrown out, one at a time, over hundreds of millions of years, by something that was standing where you are going. And you arrive at the exact center, and there is nothing there. Not a bright object you cannot resolve. Not a faint one. No X-ray point source at the limits of the deepest observation anyone has taken. The most violent excavation on record, and no evidence of the excavator. This is not a lone claim, which is worth saying, because the recoil idea sounds far-fetched until you look at the comparison cases. The Quasar 3C186, at a redshift of about 1.07, hosts a black hole of roughly 3 billion solar masses that sits 11.1 kiloparsecs from its host galaxy's center. That is about 36,000 light-years further from its galaxy's core than the Sun is from ours. It is moving at 2,140 kilometers per second relative to the galaxy. Millimeter observations found 80 billion solar masses of molecular gas sitting on the host galaxy, and none at all at the quasar's position. The black hole has left its own gas behind and is running on what it brought with it. If the recoil reading of that object is correct, then the merger that produced it radiated about 9% of the total mass involved as gravitational waves, which would make it the most energetic single event ever observed by anyone. A 2024 reanalysis found that the required geometry demands substantial fine-tuning, with only about 0.03% of the plausible parameter space fitting the observation. So it is not settled either. In 2024, the first off-nuclear tidal disruption event was found, a star torn apart 800 parsecs, about 2,600 light-years, from its host galaxy's central black hole, by a second black hole that is demonstrably not at the center. And an earlier recoil claim in a quasar called J0927 plus 2943 was conclusively refuted in 2014 by molecular gas measurements. The field is careful, and it has been wrong before, and it says so. But here is the summary position, and it is stark. There is still no direct observational confirmation of any supermassive black hole merger or any recoil kick anywhere in the sky. Not one. And the uncertainties on this particular galaxy go further down than most accounts admit. The two published measurements of the mass deficit disagree by a factor of 8, which means that even the size of the hole in the middle of this galaxy is contested. There is a wider absence standing behind this one, and it is the reason this entry sits at number 1 rather than anywhere else. The theoretical ceiling for how massive a black hole can grow by ordinary accretion is around 50 billion solar masses. The largest black holes ever measured dynamically sit near 20 to 40 billion. TON 618 is estimated at 40.7 billion, NGC 4889 at 21 billion. The black hole at the center of M87, the one that was directly imaged in 2019, is 6.5 billion. And the honest summary from the field is that no clear evidence has been found for any black hole above 10 billion solar masses, which is precisely the mass that this galaxy's core demands. So there are 3 ways out, and every one of them costs something. Either the largest black holes exist and are invisible to us, in which case a whole population of the most massive objects in the universe is unaccounted for, or the relationship between a galaxy and the black hole at its center breaks down at the top end, in which case one of the most reliable tools in extragalactic astronomy stops working exactly where we most want to use it. Or something at the center of Abell 2261 is not where it is supposed to be, and there is a black hole of tens of billions of solar masses moving through the outskirts of its own galaxy at 2,000 kilometers a second, with a few billion stars trailing behind it. All three of those are a hole in the theory, and not just a hole in a galaxy. We started this list with an object that was reported 30 times over 123 years and never existed, and the thing that made that case bearable was that the record turned out to be better than the explanation. 20 named observers, notebooks preserved for 3 centuries, and a man in Belgium who sat down in 1887 and matched each sighting to the star that caused it. The record was good enough to survive 2.5 centuries of being misread, and when someone finally read it properly, it answered. Here, the record is better than the explanation as well. It is a galaxy-scale hole, measured to within a few hundred parsecs, mapped by Hubble and modeled twice, and searched twice with the finest X-ray telescope ever flown. And there is no Strubant coming. Nobody is going to sit down with the archival data and match this absence to something that was always in the catalogue. And it ends where we were 7 entries ago, at the edge of Saturn's rings, watching a half-mile object we never once photographed, and knowing it was there only from the 1,200-kilometer scratch it left in the ice. Something clearly did the emptying. That was a charming limitation of 1 camera on 1 spacecraft. Here, it is the same sentence at 12 orders of magnitude larger, and it is not a limitation of any instrument. It is the state of the art. That is the list. 10 objects that were observed, catalogued, measured, in several cases photographed, and are not there now. A moon that was never there at all. A comet that came 6 moon distances from this planet and left on a path that mathematics cannot follow. A comet that split in half in front of witnesses and now arrives only as dust. A moonlet known solely by its scratch. A solar system's worth of dust gone in under 2 years. A nebula that went out inside 1 working life. A star of 100 suns whose fate depends on which spectrum you happen to be holding. A supergiant that did not explode. The brightest engines in the universe, switching off. And a hole 24,000 light-years across, with nothing at the bottom of it. What they share is not strangeness. It is that in every single case, the observation is better than the explanation, and the explanation is still owed. The sky is not a fixed picture that we are slowly filling in. It is a working document, and some of the entries have been crossed out, and nobody has written in the margin what happened to them. Sleep well, and good night.